Hello fellow sapiens, and welcome to Sleepless Homo. This channel is here for slow science and quiet storytelling. No hype, no wild speculation, just humble archaeology and careful history told softly. If you value this kind of long-form content, consider liking and subscribing. It helps others find their way to knowledge. And if you'd like, share in the comments how you use these stories. Do you listen at night before bed, or during the day as you work? However you join me, know that if you drift off mid-chapter, I've placed timestamps in the description so you can pick up right where you left off, because the story is worth hearing all the way through. And as always, stay curious, stay calm. If you were to stand today on one of the polished wooden boardwalks that wind through Yellowstone National Park, you might think you're visiting one of the most carefully managed gardens on Earth. The rails keep you safe. The signs tell you where to look. The pathways guide you past steaming pools and turquoise waters that look as though they belong in a painter's imagination. Yet beneath the planks, only a few centimetres under the soles of your shoes, there is no true safety. What rises there is not a decorative pond, but the breathing skin of a living planet, exhaling through vents, cracks, and shifting pools. What we see as beauty is in fact one of the most hazardous landscapes ever preserved for human visitors. The first signs of what lies beneath Yellowstone are not hidden in distant catastrophes. They are here, bubbling up softly, almost politely, as if the earth itself were testing how much we notice. It is a strange paradox. The most dangerous feature in Yellowstone is not the bear that might cross your path, or the bison that might block the road. It is water. Superheated water forced from the ground at temperatures well above the point where it would boil in your kitchen. Geysers, mud pots, fumaroles, and hot springs are not side attractions. They are the outward symptoms of an immense reservoir of heat, rising from far below. And yet, they appear in colours that seduce us into forgetting their danger. Grand Prismatic Spring, with its rainbow rings of thermophiles, looks like a cosmic eye staring back at us, but the water that fills it can sear flesh in a second. Over the years, there have been accidents, some fatal, when visitors stepped off the boardwalk, slipped, or underestimated how thin the crust can be. This landscape is never static. A place that looks solid may in fact be little more than a film of silica over boiling water. What we call the surface here is only a suggestion. So what do these features reveal? They tell us that heat is constantly leaking to the surface, and not in small amounts. Geologists measure Yellowstone's heat flow as more than 30 times the background rate of the entire Rocky Mountain region. That kind of output is not the work of an ordinary geothermal system. It is sustained by something vast and enduring. Each geyser eruption is not simply a show for tourists, but a tiny pressure valve for Earth's interior. The plumes of steam, the violent spouts, the quiet simmer of a hot spring, all of them are sending us a reminder the heat below has not gone away. Take Steamboat Geyser in Norris Basin. It is the tallest geyser on the planet, capable of blasting columns of water more than 100 meters into the sky. For decades at a time it can remain silent, then without clear reason it will enter a phase of frequent eruptions, as it did in 2018. Each blast is unpredictable, a chaotic reaction to pressure building in subterranean channels. Scientists still struggle to model why it behaves so erratically. That very unpredictability is the message. Yellowstone's hydrothermal system is not easily understood because it is governed by pressures, fractures, and mineral deposits that change constantly. We are watching a machine with too many hidden gears to predict. These thermal features also act as sensors. By studying the chemistry of the waters and gases that rise from them, researchers can trace what is happening deeper down. Carbon dioxide, hydrogen sulfide, and sulfur dioxide seep upward in varying ratios, hinting at magma and rock interactions far beneath the ground. For example, when more carbon dioxide emerges than models can explain from the shallow chamber alone, it tells geologists that there must be deeper reservoirs feeding the system. The surface chemistry is a code, a kind of volcanic Morse signal, flashing through vents and pools for those who know how to listen. But the code is never simple. It shifts with rainfall, with seasonal snowmelt, even with earthquakes hundreds of miles away. The hazards are not theoretical. Hydrothermal explosions have occurred throughout Yellowstone's history. These are not eruptions in the Hollywood sense, with lava fountains and rivers of fire. but they can be just as deadly on a local scale. Imagine superheated water trapped beneath a sealed layer of rock. When the pressure is released suddenly, the water flashes to steam, blowing rock and mud outward with the force of a battlefield shell. One such event left Mary Bay on Yellowstone Lake as a vast hydrothermal crater. Others are smaller but still dangerous, like the explosions that created new pools in Norris Geyser Basin as recently as the winter of 2024 to 2025. Scientists traced those events through infrasound detectors and satellite images, reminding us that the ground is fragile, constantly rearranging its plumbing. These changes do not mean a global catastrophe is imminent. They mean the park is alive, reshaping itself beneath our feet, reminding us not to mistake the boardwalk for safety. Even the colours of the pools whisper geology. The greens and oranges at the edges of springs come from thermophiles, organisms that thrive in near-boiling conditions. They are survivors from Earth's early chapters, lineages that may stretch back billions of years. To the untrained eye, they make the water beautiful. To the geologist, they announce that Yellowstone is not only a stage for danger, but also a laboratory for resilience. The fact that life thrives here, in conditions that would kill us instantly, is proof that Earth's extremes are more habitable than we once imagined. These microbes have also given us tools like the polymerase chain reaction, a technique that reshaped medicine and genetics. It is a quiet reminder that the hazards and wonders of Yellowstone are inseparable. The same heat that threatens to scald is also what nurtures organisms that have transformed science. Standing on a boardwalk watching steam curl into the sky, you might think nothing is happening. But the truth is that every wisp is evidence of a constant transfer of energy from Earth's depths to its surface. Each hiss of steam is the outcome of water circulating thousands of meters down, heating, dissolving minerals and rising again. It is a planetary engine venting into the open air. What makes Yellowstone extraordinary is not simply that it has geysers or hot springs. It is the scale of the system. No other place on Earth's continents channels so much geothermal energy to the surface in such a small region. That concentration of heat is what makes Yellowstone simultaneously dangerous and mesmerizing. And so, the first signs we miss are not subtle at all. They're right in front of us, advertised in colours, sounds, and smells. But we become distracted by their beauty, treating them as harmless attractions rather than geological warnings. Yellowstone has always been dynamic. Pools appear and vanish, geysers shift their behaviour, the ground itself lifts and subsides by centimetres each year. If you only saw the postcards, you might imagine permanence. If you walk the trails with your eyes open, you notice instability. The Earth here does not hide its restlessness. It sings it in boiling water and sulphur-scented steam. The haunting question, then, is not whether Yellowstone will one day erupt in unimaginable violence. It is whether we are listening to what it tells us every single day. The first signs are not in distant futures. They are beneath the boardwalk where the Earth whispers through water and heat, waiting to see if we pay attention. There is another layer of meaning in these pools that often goes unnoticed. The hydrothermal fields of Yellowstone are not just decorative accidents, they are records of energy exchange. When scientists measure the temperature of a hot spring or the flow of a geyser, they are essentially measuring the pulse of the planet in real time. Unlike the rocks and cliffs, which change on timescales of thousands or millions of years, these thermal features shift by the season, sometimes by the week. In a way, they are the most immediate expression of Earth's hidden processes, flickering like indicators on a dashboard. If a spring grows hotter, or a geyser falls silent, the system is adjusting itself. It does not necessarily mean disaster is near, but it does mean that the ground below is reconfiguring. The boardwalks may feel timeless, but the landscape around them is never the same 2 years in a row. For people who lived in this region long before national parks existed, these signs were not taken lightly. Archaeological evidence shows that indigenous groups have been visiting the hot springs for at least 11,000 years, leaving behind obsidian tools and campsites. Oral traditions often describe the geysers and pools as sacred places, imbued with spirits or powers that could not be approached carelessly. Modern science may use instruments instead of stories, but the message is similar. This is not ordinary ground. Respecting the landscape is part of survival here. In that sense, the warning signs have always been present, whether interpreted through mythology or through seismographs. One striking detail is how sensitive these features are to events far away. A strong earthquake in Alaska or a distant tectonic shift can alter the behaviour of Yellowstone's geysers within days. Channels collapse, water tables adjust, and suddenly a familiar spout erupts differently. This interconnectedness shows us that Yellowstone is not an isolated pot simmering on its own. It is tied into the greater system of North American geology, a reminder that the crust beneath us is an interwoven fabric, tugged and stretched across vast distances. What looks like a single park on a map is actually a node in a much larger network of forces. It is also worth noting that hydrothermal activity does more than decorate the land, it sculpts it. The silica deposits that form terraces at Mammoth Hot Springs are built grain by grain, as steaming water leaves behind dissolved minerals. Whole hillsides are gradually constructed this way, then abandoned when channels shift, leaving ghostly white formations that look like frozen waterfalls. In other places, acid sulfate pools dissolve the rock itself, carving pits and cavities that collapse without warning. When we speak of Yellowstone changing, it is not only the eruptions we imagine in the far future. It is the quiet work of chemistry and water happening now, reshaping valleys and basins in front of us. And so, the lesson from beneath the boardwalk is not only about danger, but also about motion. Yellowstone refuses stillness. Its geysers, springs, and steaming vents are constant reminders that the surface we stand on is a thin and temporary crust, stretched over forces that will always find a way through. If there is comfort in this, it is the knowledge that the Earth has been speaking this way for millions of years, and humanity has so far managed to listen, sometimes in fear, sometimes in awe. Perhaps the only real question is whether we can continue listening carefully enough to notice what the water and steam are trying to say before the next change arrives. On the night of August 17th, 1959, Yellowstone's calm mask slipped. What had been a summer evening of camping under the stars turned into one of the most violent geological events in American memory. The setting was Hebgen Lake, just west of Yellowstone National Park, where families and vacationers had gathered in the warm season to fish, hike, and sleep in tents along the water. At 11:37 p.m., without warning, the ground heaved. What followed was a moment of sudden violence that reminded scientists and visitors alike that Yellowstone was not a quiet postcard, but a restless engine hidden under thin soil and forest. The quake that struck that night measured 7.3 in magnitude. In geological terms, that is not the largest earthquake ever recorded in North America, but its consequences were extraordinary because of the setting. The Madison River Canyon, steep and unstable, gave way almost instantly. 80 million tons of rock, trees and debris collapsed in a matter of seconds, crashing down upon campsites filled with people who had only moments earlier been roasting marshmallows or rolling into sleeping bags. The landslide thundered across the canyon and slammed into the valley floor, creating a natural dam that blocked the Madison River. In that instant, Hebgen Lake rose, surged, and spilled. Campers had no time to react. Entire sections of River Valley were buried beneath a wall of the rock. 28 people lost their lives that night. 19 of their bodies were never recovered, entombed under the landslide that geologists later calculated to be one of the largest ever triggered by an earthquake in the continental United States. Survivors told stories of the earth groaning, of boulders crashing through trees in the darkness, and of waves in Hebgen Lake so large they destroyed cabins and boats along the shore. Roads split open, sections of highway dropped several meters, and bridges twisted like paper. To those who lived through it, the quake was not an abstract number on a seismograph, but a force that reshaped the landscape in front of their eyes. For scientists, the quake was equally shocking. Until that moment, Yellowstone had largely been treated as a stable geological wonderland. The focus had been on its geysers, hot springs and wildlife, but few had thought of it as a place where catastrophic geological violence could erupt in modern times. The 1959 quake changed that perception overnight. Suddenly, the region was recognised not only as a geothermal showpiece, but also as one of the most seismically active zones in the American interior. The park and its surroundings had not experienced such devastation in recorded memory, and the question shifted from whether Yellowstone was alive to just how active it really was. One of the most visible legacies of that night is Earthquake Lake, or Quake Lake, which still sits in the Madison Canyon. Formed by the natural dam created by the landslide, it remains a reminder that landscapes can change in minutes. What had once been forest and campsites became a drowned valley, dotted with dead trees still standing eerily in the water decades later. Tourists driving through the region today can stop at interpretive sites that tell the story, but at the time there was no guide, only shock. The event made clear that Yellowstone's foundations were not ancient stone frozen in time but fragile crust strained by forces below. Geologists rushed to the region in the aftermath. Among them were researchers from the US Geological Survey, who quickly set up networks of instruments to record aftershocks. They discovered that the quake was not an isolated event but part of a complex system of faults. Hundreds of aftershocks rattled the area in the weeks that followed, some strong enough to further unsettle already traumatized survivors. The data they collected helped establish Yellowstone as one of the most earthquake-prone regions in the western United States, with more than 1,000 measurable quakes occurring each year. What the 1959 disaster did was push this fact into public consciousness. Beyond the raw seismic numbers, there was another revelation. The landslide and uplift patterns around Hebgen Lake hinted that something more than shallow faulting might be involved. The crust in the Yellowstone region seemed thinner, more easily deformed, and more dynamic than expected. While scientists did not yet speak of supervolcanoes or deep magma reservoirs, the suspicion began to grow that the region's unusual hydrothermal activity and its seismic restlessness were not separate mysteries. They were linked expressions of the same heat source buried far below. The quake also transformed how emergency management was understood in Yellowstone. Rangers and geologists realized that a place marketed as a natural playground was in fact layered with risks not visible to casual visitors. Signs went up warning about unstable slopes, and monitoring increased in places that had once seemed quiet. The event spurred conversations about how to prepare for future geological hazards in national parks, conversations that continue to this day. For the local communities, the earthquake was not only a scientific event but a human tragedy. Families grieved, loved ones lost in the dark. Survivors rebuilt homes along Hebgen Lake, but the memory of that night lingered. Oral histories passed down among residents recall the fear and confusion, the sound of rocks falling like thunder, and the strange silence afterward as dust settled and survivors realized entire campgrounds were gone. In many ways, the quake brought home the reality that living near Yellowstone meant living beside a restless Earth. And yet, there is humility in admitting what we still do not know. Geologists have studied the 1959 event for decades, tracing fault lines and modelling landslide mechanics, but predicting when or where another quake of similar size might occur is beyond current science. Yellowstone continues to record swarms of smaller quakes every year, most harmless. But the lesson of Hebgen Lake is that the ground can shift catastrophically without giving humans much warning. The event was not caused by the magma system directly, but by the fragility of the crust above it, reminding us that Yellowstone's hazards are varied and not confined to the scenarios people most fear. Today, visitors who walk along Quake Lake or drive through Madison Canyon may pause at signs that tell of the night the campers vanished. The stillness of the water and the quiet of the forest make it hard to imagine the chaos that once unfolded there. But the landscape remembers. It is scarred by fault lines, by tilted cabins preserved as memorials, by ghostly tree trunks standing in water that should never have been there. These are not just curiosities for tourists. They are lessons carved into the earth about the speed at which change can arrive. The haunting question that remains is simple. If a quake of that size could take lives, reshape rivers, and rewrite scientific assumptions in a matter of minutes, what else might Yellowstone hold in its restless depths? The 1959 earthquake did not answer that question, but it forced us to start asking it. If you ask a child to draw a volcano, the pencil almost always shapes itself into a cone. The image is universal, a steep mountain with a smoking crater at its summit. Mount Fuji, Vesuvius, Kilimanjaro, Stromboli. All of them conform to the silhouette that seems to define the very idea of a volcano. And yet when geologists in the mid-20th century began to ask where Yellowstone's volcano was hiding, they could find no cone, no peak, no tidy mountain announcing its existence. There were geysers and hot springs, earthquakes and strange ground movement, but none of the architectural features that usually give away a volcanic edifice. This puzzle would occupy years of fieldwork, miles of survey lines and countless sheets of paper filled with contour sketches. It would lead to one of the most startling revelations in American geology. Yellowstone's volcano was so large it had swallowed its own cone and left behind a hole too vast for the human eye to comprehend at ground level. The quest to understand this hidden feature gained momentum in the 1960s, spurred by the aftermath of the Hebgen Lake earthquake. That disaster had already forced scientists to admit that Yellowstone was not geologically dormant. The question was how alive it truly was. Enter Robert Bob Christensen, a geologist with the US Geological Survey, who would devote years of his career to solving the riddle of Yellowstone's missing volcano. He began in the only way possible at the time, by walking the ground, climbing ridges, and mapping rock layers one outcrop at a time. In an era before drones, GPS, and computer modelling, the geologist's toolkit was a compass, an altimeter, aerial photographs, and stubborn patience. What Christensen and his colleagues noticed almost immediately was that Yellowstone's bedrock was blanketed by thick deposits of volcanic ash and welded tuffs, layers of material that could only have come from immense explosive eruptions. These deposits were tens of meters thick, stretching across valleys and ridgelines, sometimes altered into pastel colours by hot waters that had percolated through them for millennia. They did not resemble the lava flows of ordinary eruptions, but sheets of pulverized rock and glass welded together by heat. Their volume suggested events on a scale far beyond any known in recent human history. The rocks told the story of a colossal release of energy, yet no single mountain could be identified as the source. The solution began to emerge as Christensen carefully plotted the distribution of these volcanic deposits and traced their angles and boundaries. Instead of pointing back to a central cone, the layers curved and dipped around vast depressions in the landscape. Valleys and ridges seemed to form arcs rather than straight lines. Rivers bent around inexplicable curves. The aerial photographs showed features that were difficult to perceive while standing on the ground. Broad, shallow bowls in the landscape that spanned dozens of kilometres. What looked like ordinary valleys began to reveal themselves as the edges of something larger. After years of painstaking work, Christensen proposed what at the time was a radical conclusion. Yellowstone had not one, but multiple calderas. Gigantic depressions formed when massive volumes of magma erupted, and the ground above collapsed into the empty space. These calderas were not small. One measured more than 60 kilometres across, another about 40 kilometres, overlapping like scars from repeated wounds. They were so large that a person standing within them could not see their outlines. Only from an aircraft could the true shape of the terrain be appreciated, and even then the scale was so immense that it stretched the imagination. This was not a volcano in the familiar sense. It was a complex of overlapping craters, each one the remnant of an eruption that dwarfed any in recorded human history. The recognition of Yellowstone as a caldera system fundamentally shifted the understanding of volcanism in North America. It suggested that eruptions here were not ordinary events but continent-shaping cataclysms. At the time, the word supervolcano was not yet in popular use, but the concept was born from discoveries like these. Christensen's maps showed that the central region of Yellowstone National Park, including places now famous for their hydrothermal wonders, sat within the margins of these ancient calderas. The geyser basins and hot springs were not random decorations, but direct evidence of the still-warm scars left behind. Each basin occupied fractures and weak zones created when the ground collapsed during those ancient eruptions. Water seeped down, heated by residual magma, and returned to the surface as steam and boiling springs. The hydrothermal beauty that tourists admired was, in truth, the afterglow of apocalyptic events. To appreciate the scale of the discovery, it is useful to compare it to known eruptions of the modern era. Mount St. Helens in 1980 produced 7 billion tons of material. The deposits mapped by Christensen represented hundreds to thousands of times that volume, enough to blanket entire states under meters of ash, enough to darken skies across continents. and yet all of it had happened long before people kept written records, leaving only rocks and depressions as testimony. The mapping work of the 1960s and 70s was not glamorous. It involved trudging over remote ridges, sleeping in tents, poring over topographic maps by lantern light, and checking and rechecking the orientation of tiny crystals under microscopes to match ash layers across miles. But the cumulative result was a revelation. Yellowstone's missing volcano was not a cone waiting to be identified. It was an absence, a negative form, a hole too big to see without stepping far outside of it. This recognition also forced a rethinking of hazard assessment. Until then, the assumption had been that Yellowstone was a beautiful, eccentric geothermal area, but not necessarily one of global consequence. Christensen's work suggested otherwise. If such eruptions had occurred multiple times in the geologically recent past, then the possibility existed, however remote in human timescales, that they could occur again. The question was no longer whether Yellowstone had a volcano, but what kind of volcano it truly was, and what its history implied about its future. Yet it is important to be humble about the limits of what could be known at that time. Christensen and his peers did not have modern seismic imaging. They could not peer into the crust to see magma bodies directly. Their interpretations were based on surface rocks, field relationships, and aerial photographs. There were debates, revisions, and uncertainties, but the weight of evidence kept pointing toward the same conclusion. Yellowstone's landscape had been carved by explosions of a magnitude difficult even for geologists to accept. The legacy of those mapping campaigns still shapes scientific understanding today. Every visitor who drives across the broad plateaus of central Yellowstone, from Old Faithful to Yellowstone Lake, is in fact traversing the floor of a collapsed volcanic crater, even if there are no sharp rim walls to signal it. The forests and meadows conceal the scars, but the rocks beneath them still whisper of collapse and fire. And so the story of the caldera is a lesson in scale. Human senses are tuned to mountains and rivers, to features we can see from a single vantage point. Yellowstone defies that intuition. To understand it requires stepping back, piecing together clues over vast distances, and recognizing that sometimes the greatest features on Earth are not peaks that rise, but voids that remain. The haunting question that remains is whether we can ever truly see such features clearly without the benefit of catastrophe. Christensen could only map what was already revealed by ancient violence. The present gives us no such vantage point. We walk in valleys, camp beside lakes, and marvel at geysers, all within a crater whose edges lie beyond the horizon. If Yellowstone's past eruptions reshaped entire landscapes beyond human recognition, what might its future still hold, hidden just out of sight? How do you measure an explosion so vast that it reshapes half a continent? With most volcanoes, we can walk to the crater rim, measure the lava flows and weigh the ash deposits. But in Yellowstone, the craters are too large to see in their entirety, and the ash fell across distances measured not in valleys or states, but in time zones. The story of Yellowstone's 3 super-eruptions is told not by a single mountain, but by scars spread across the western United States. Scars so broad that they appear only when geologists begin counting layers of ash and tracing them across thousands of kilometers. These 3 events, 2 million years ago, 1.3 million years ago, and 640,000 years ago, define Yellowstone's volcanic history. They are not equal in size or impact, but together they mark Yellowstone as a place where eruptions did not merely form mountains but dismantled them. The first of these eruptions took place about 2,100,000 years ago. It left behind what scientists call the Huckleberry Ridge Tuff, a sheet of volcanic rock so thick and extensive that it remains one of the largest known volcanic deposits on Earth. The eruption is estimated to have expelled more than 2,500 cubic kilometers of material. To put that in perspective, the eruption of Mount St. Helens in 1980 produced just 1 cubic kilometer. Even Krakatoa, famous for the global reverberations of its 1883 eruption, generated only about 20 cubic kilometers. The Huckleberry Ridge event was, in terms of sheer volume, over 100 times larger than Krakatoa. Geologists estimate that this eruption excavated a caldera more than 60 kilometers across, setting the template for Yellowstone's later history of collapse and renewal. roughly 800,000 years later, another eruption reshaped the plateau. About 1.3 million years ago, the Mesa Falls eruption sent more than 280 cubic kilometers of ash and debris into the air. While smaller than the Huckleberry Ridge blast, it was still enormous compared to ordinary eruptions. Its deposits, known as the Mesa Falls Tuff, can be traced across the region like pages in a geological ledger. They preserve evidence of a pyroclastic flow that travelled at hurricane speeds, flattening forests and scouring landscapes far beyond the immediate caldera. The scar it left behind is the Henry's Fork caldera in Idaho, a reminder that Yellowstone's volcanic system does not respect park boundaries but sprawls across multiple states. The third and most recent super-eruption took place about 640,000 years ago, producing the Lava Creek Tuff. This eruption released about 1,000 cubic kilometers of material and created the present-day Yellowstone caldera, a depression about 70 by 45 kilometers in size. When visitors stand today at Yellowstone Lake or drive across Hayden Valley, they are inside the vast bowl left behind by this eruption, though the rim is so subtle that only maps and satellite images reveal its true scope. The Lava Creek eruption spread ash across much of North America. Geologists have identified its chemical fingerprint in sediments as far away as the Gulf of Mexico. It was a continental-scale event, the kind of eruption that would dominate every human record if it had occurred within our species' memory. These three eruptions are often spoken of together, but it is important to remember that they were separated by immense spans of time. 2,100,000 years ago, when the Huckleberry Ridge eruption occurred, early members of the genus Homo were just beginning to fashion stone tools in Africa. By the time of the Lava Creek eruption, our own species, Homo sapiens, had not yet evolved. From the perspective of human history, each eruption is staggeringly ancient. What makes them relevant is not that they occur frequently on our scale, but that their recurrence demonstrates Yellowstone's capacity for repetition. Geologists use these events to classify Yellowstone as a supervolcano, a term that refers to eruptions with volumes greater than 1,000 cubic kilometers. While the word is sometimes used carelessly in popular culture, the underlying definition is precise. The fact that Yellowstone has produced 3 such eruptions in the last 2 million years places it among a very small group of volcanic systems on Earth capable of reshaping entire continents in a single event. These eruptions are not annual or even millennial. They are pulses of planetary energy released on timescales that dwarf human civilizations. To measure eruptions of this scale, scientists rely on multiple lines of evidence. They examine the thickness and extent of tuff layers, use radiometric dating to establish ages, and match the geochemistry of ash deposits across vast regions. When the chemical signature of Yellowstone's eruptions is found in sediment cores from distant sites, it provides confirmation that the ash clouds reached continental scales. The rocks are the only witnesses, silent but precise. Yet the magnitude of these eruptions also raises questions that geologists cannot yet fully answer. Why do some volcanic systems release energy gradually, through frequent smaller eruptions, while others accumulate it for hundreds of thousands of years before discharging it catastrophically? Why did Yellowstone erupt at these 3 particular intervals, and why has it remained comparatively quiet for the past 640,000 years? These are not questions of folklore but of physics, involving the buoyancy of magma, the strength of the crust, and the dynamics of heat rising from Earth's mantle. What we do know is that Yellowstone's 3 eruptions are distinct in scale, but united in consequence. Each one left behind a caldera, each one buried landscapes under meters of ash, and each one reminds us that the forces shaping the Yellowstone Plateau are not subtle, but explosive. When we walk today through forests, past meadows and along lake shores, we're walking on ground that once collapsed into itself after discharging energy beyond human comprehension. And yet, humility requires us to admit that our perspective is limited. To speak of 3 eruptions is to compress 2 million years of history into a handful of data points. There may have been smaller eruptions between them, events erased by erosion, or difficult to distinguish in the geologic record. The Earth does not keep archives for our convenience. It leaves behind scattered evidence, and we piece together the story as best we can. So the haunting question is not only about when or if another eruption might occur, It is about what kind of system we are dealing with. Is Yellowstone's history of 3 super-eruptions the rule or the exception? Are we glimpsing a regular rhythm, or merely catching fragments of a much more complex song? The rocks give us a timeline, but not a pattern we can trust with certainty. What we have is evidence of power, scars on the landscape, and a reminder that the world we inhabit is shaped as much by what it destroys as by what it builds. There is another way to grasp the enormity of Yellowstone's 3 eruptions, and it comes not from looking across the land but from looking down into its debris. In quarries and road cuts scattered across the west, geologists find layers of ash turned to stone that tell of days when the sky itself collapsed. These are not fine, gentle powders like the dust from a campfire. They are welded tufts, rock that was once a searing mixture of gas, ash and shattered crystals, moving faster than any hurricane. When it settled, it did so hot enough to fuse into sheets of glassy stone. In places, the flows are more than 100 meters thick, draping entire mountain slopes and valleys. To stand inside a canyon carved through one of these deposits is to stand inside a time capsule of violence, a frozen memory of minutes that unfolded long before humans walked this continent. One often overlooked detail is how each eruption left behind subtle but permanent changes in the region's topography. The Huckleberry Ridge event, for example, did not merely expel unimaginable volumes of material, it created a caldera so broad that it altered river courses and drainage systems, setting the stage for later landscapes. The Mesa Falls eruption reshaped what is now eastern Idaho, creating the Henry's Fork caldera that remains visible today as a broad depression ringed by younger volcanic features. The Lava Creek eruption produced the caldera we now call Yellowstone, and the outline of that scar still dictates where lakes form, where forests grow, and where geothermal activity concentrates. These eruptions did not end when the ash settled. They rewrote the map in ways that endure hundreds of thousands of years later. Another way scientists have come to appreciate their scale is by comparing them to events beyond North America. The eruption of Tambora in 1815, often cited as the largest in recorded human history, darkened skies around the globe and caused crop failures from Europe to China. It expelled about 160 cubic kilometers of material. Impressive by human standards, yet each of Yellowstone's eruptions surpassed it many times over. This comparison helps ground our imagination. The greatest disaster in modern history was, in geological terms, a minor cousin to the events that shaped Yellowstone. It is also worth remembering that Yellowstone's volcanic history is not defined only by these 3 giants. Between them, smaller lava flows spread across the plateau, building up domes and ridges that now host forests and meadows. These quieter eruptions, though lacking the drama of super-eruptions, remind us that Yellowstone has more than one mode of expression. Its personality is not limited to cataclysm. It can also build slowly, releasing magma in steady pulses that contribute to the plateau's bulk. In a sense, the 3 great eruptions stand out not because they were Yellowstone's only voice, but because they were the loudest verses in a much longer song. When pieced together, these threads give us a picture of a system that breathes on timescales far beyond our comprehension. The 3 super-eruptions are like punctuation marks in a manuscript still being written. They show that Earth is capable of acts of extraordinary violence, but they also reveal a continuity, a persistence of volcanic energy beneath the Yellowstone Plateau stretching back millions of years. The haunting thought is not only what another eruption might mean, but how little of the manuscript we have read. We are glimpsing a story that began long before us, and will continue long after, and the scars we count are just the few sentences that survived. Imagine standing on a hillside watching a column of ash rise into the sky, thinking you're at a safe distance from a volcano. The sound is deafening, the light strange, but you still feel grounded in reality, until the mountain itself begins to collapse. Out of the base of the eruption comes not a plume, but a wall, a boiling avalanche of ash, gas, and shattered rock fragments. It does not rise gently into the atmosphere. It charges outward, hugging the ground, moving faster than any animal can run, and hotter than any fire humanity has ever controlled. To call it a flow is misleading, because it behaves less like water and more like a hurricane turned solid, a storm that incinerates as it goes. Scientists have given this phenomenon a clinical name: pyroclastic density current. But for those who have seen it firsthand, the words that come to mind are simpler: fire, suffocation, obliteration. We know what these currents look like because history has preserved examples in stone and in memory. In the year 79 of the Common Era, the eruption of Vesuvius overwhelmed the Roman towns of Pompeii and Herculaneum. For centuries, the popular imagination focused on the rain of ash that buried the cities, yet it was the pyroclastic surges that delivered the most immediate horror. In Herculaneum, the waterfront was lined with vaulted chambers where hundreds of people sought shelter. When excavations uncovered these vaults, the skeletons lay in positions that spoke of sudden agony. The searing heat arrived so quickly that flesh vaporized, leaving bones fractured and skulls burst from internal steam. In Pompeii, people collapsed in the streets, asphyxiated by a choking cloud that pressed down like an invisible sea. The plaster casts we see today are not statues of slow burial, but the imprints of lives extinguished in moments by a storm of ash and fire. In more recent times, the Caribbean island of Montserrat lived through the same terror. During the 1990s, its Soufriere Hills volcano erupted in a series of surges that raced down slopes at speeds over 100 kilometers per hour. Filmmakers captured flows glowing at night, cascading like rivers of fire into the sea, generating their own thunder. The capital city of Plymouth, once home to thousands, was erased. Streets disappeared under meters of hot debris, roofs collapsed, and the town was left entombed in a silence that mirrored Pompeii's fate 2,000 years before. Survivors spoke of the sound, like a freight train combined with breaking surf, and the impossible heat that ignited everything it touched. Even those who escaped could not shake the memory that their city had been removed not by an earthquake or by lava, but by a storm that behaved like no other force of nature. Mount St. Helens in Washington state gave another glimpse in 1980. Its eruption blasted sideways, releasing a pyroclastic surge that leveled forests across nearly 600 square kilometers. Entire slopes of evergreens were mowed down in the same direction, like blades of grass under a scythe. The initial blast was visible, but the true destruction came in the grey cloud that rolled across the land, carrying both crushing force and suffocating heat. Scientists who later studied the deposits found evidence of temperatures high enough to ignite living tissue instantly. It was not just the velocity, but the density of the flow, filled with shards of volcanic glass, that made survival impossible. Each of these events was devastating in its own right, yet they also serve as laboratories for understanding something even more immense. What happens when the energy driving a pyroclastic current is not measured in cubic kilometers of material, but in hundreds or thousands of cubic kilometers? At Yellowstone, the record shows that pyroclastic flows once swept across entire states, blanketing terrain in welded tuff that remains visible in cliffs and road cuts today. These deposits tell us that the surges did not simply pour outward like rivers. They billowed, pulsed, and spread over landscapes far larger than a single valley. The haunting part is imagining the human perspective. If standing on the hills above Pompeii meant watching a surge in the distance, then standing within Yellowstone's range would mean watching the horizon itself turn into a wall. The scale is almost beyond comprehension, not because the physics are different, but because the size of the chamber feeding the eruption gives that physics more fuel than the mind can grasp. It becomes clear that flow is the wrong word. What we are describing is a ground-hugging storm, a hurricane of rock that blots out not just the sun, but the idea of safety. For scientists, pyroclastic flows remain among the most difficult volcanic phenomena to model. They move too fast for ordinary measurement, too hot for instruments to survive, and too unpredictable for direct observation. Computer models and field studies give us clues. Surges stratify into turbulent tops and denser bases. The gases within them vibrate like organ pipes, and the deposits reveal sudden shifts in direction. But there is humility in admitting how little we can reconstruct about their interior. They are in a sense the black boxes of volcanic eruptions, recording immense energy in forms we can only glimpse through their aftermath. So what does it feel like when the ground itself becomes a storm? We do not fully know except through echoes left in bones, ruins and scorched landscapes. The truth is that pyroclastic flows are not events one experiences and retells. They are events that erase the very possibility of memory. That silence is perhaps their most chilling feature. They do not simply kill, they erase whole conversations, communities, and moments of life, leaving behind only a hardened record in stone. Which leads to a question that lingers long after the science is explained. If the Earth can unleash a storm that swallows memory itself, how do we prepare for something that cannot be remembered by those who endure it? Another perspective on these fiery avalanches comes from looking at the land they leave behind rather than the moment they sweep through. In the Valley of 10,000 Smokes in Alaska, the eruption of Nova Rupta in 1912 sent pyroclastic flows racing across the landscape. Unlike the Roman ruins or the destroyed towns of Montserrat, this valley became a kind of natural museum, a place where the deposits were left in plain sight. What researchers found was astonishing. In some places, the pyroclastic material was more than 200 metres thick, enough to bury entire valleys and change their ecology for generations. Even a century later, steam vents rise from the hardened surface, reminding us that the energy of that single eruption has not entirely dissipated. The flows were so vast that rivers had to carve entirely new channels, demonstrating that these storms do not simply pass through, they reset the rules of the landscape. Studying deposits like these has also given scientists a rare window into the mechanics of pyroclastic flows. Layers within the hardened tuff show how surges can come in waves, each pulse laying down a different texture, some coarse with pumice, others fine with ash. It is as if the eruption breathes, releasing violent bursts in rhythm, not one continuous flood but a series of pulses. This detail helps explain why some victims of eruptions appear to have had moments between surges to move or attempt escape, only to be caught by the next pulse. The flows are not only deadly storms but complex systems with shifting behaviour that remains hard to predict even with modern models. Animal remains also add to the story. Fossil beds from prehistoric eruptions preserve not only the stone and ash, but also the sudden absence of entire ecosystems. In these cases, pyroclastic flows were not selective. Forests, grasslands, rivers, all were buried under a uniform blanket. In some deposits, the absence of organic material is so complete that geologists describe them as sterilized zones, as if nature itself had been erased. The haunting implication is that survival is not a matter of strength or speed. Once the storm begins, biology offers no advantage, and yet, life does return. The slopes of Mount St. Helens are now covered in young forests, and wildlife has found its way back into the Valley of 10,000 Smokes. This resilience should not obscure the violence of the original event, but it does remind us that Earth's surface is a place of cycles. Pyroclastic flows may wipe the slate clean, but that slate eventually fills again. For humans, however, the timescale of recovery can stretch beyond memory. What nature rebuilds in a century, societies cannot easily outlast. The real question, then, is not only how to understand these volcanic storms, but how to live in a world where they are possible. If landscapes themselves can be rewritten in minutes, what does that mean for the permanence we imagine in our towns, our histories, our stories? Perhaps the lesson of pyroclastic flows is that permanence is the illusion, and the storm is the reality that occasionally surfaces, reminding us how provisional our foothold on the land really is. It is one thing to imagine a volcanic catastrophe devastating the land immediately around it. It is another to realize that sometimes the most enduring tragedies unfold hundreds or even thousands of miles away, long after the roar has faded. On the rolling plains of Nebraska, far from any volcano today, paleontologists have uncovered a scene that reads like the closing act of a slow and merciless disaster. Here, in the layers of sediment now exposed by quarries and gullies, lies a graveyard of ancient animals. Horses, camels, and even rhinoceroses once roamed these grasslands during the Miocene epoch, about 12 million years ago. They were thriving, grazing by rivers, congregating at waterholes. Then, seemingly without warning, they died together in great numbers, their skeletons preserved in positions that betray suffering rather than sudden impact. What silenced them was not a predator or drought, but the breath of a distant volcano, erupting in what is now Idaho. The ash that drifted across the Great Plains was deceptively fine, more like powdered glass than soil. Blown high into the atmosphere, it rode the winds eastward until it fell upon Nebraska like invisible snow. Unlike the coarse fragments that fall near an eruption, this ash was microscopic, its particles small enough to infiltrate lungs and lodge deep within delicate tissues. At first, the animals would have kept grazing, unaware that each breath carried in a new shard. Days would pass, then weeks. Slowly they began to choke, not by sudden suffocation but by a disease that grew bone where no bone should be. When paleontologist Michael Voorhees began studying the site known as ashfall fossil beds, he was struck by the peculiar condition of the skeletons. Many bore signs of abnormal bone growth, porous and spongy layers that encrusted jaws and ribs. This was evidence of a rare syndrome known as Marie's disease, a reaction to prolonged irritation of the lungs. The inhaled ash had inflamed and scarred the animals' respiratory systems. Their bodies responded by laying down new bone in a desperate and doomed attempt to adapt. The result was agony that left unmistakable marks in the fossil record. This was not instant annihilation like Pompeii. It was slow-motion mortality, a second death after the first insult of breathing poisoned air. The tragedy is made more haunting by the order in which the animals perished. At the site, smaller creatures like birds and turtles are found at the bottom of the ashbed, felled quickly by the first waves of suffocating dust. Larger animals, horses, camels, rhinos, succumbed later, their skeletons layered above, as though they had lingered a little longer, weakened by weeks of poisoned lungs before collapsing. Many were found near what had been the edge of a watering hole. Like people grasping for breath, they had been drawn to the water, only to die in clusters at the same place. The ash did not only kill, it staged a cruel illusion of hope, luring animals to water they could no longer swallow, ending their lives in a mass grave that we now excavate as if it were a crime scene. The Nebraska graveyard tells us something crucial about volcanic hazards. Distance is not safety. The volcano responsible was more than 1,000 miles away, yet its breath was strong enough to alter ecosystems on the other side of a continent. And this was not a Yellowstone super-eruption. It was a lesser eruption by comparison, though immense by human scales, sending enough fine particles into the wind to poison animals across entire prairies. The fossils remind us that the reach of ash is not measured only in thickness on rooftops, but in invisible damage to lungs, to food webs, and to the hidden mechanics of survival. There is also a subtle irony in how the ash preserved what it killed. The same particles that clogged lungs and spurred bone disease eventually blanketed the bodies, sealing them away from scavengers and decay. Over time, rivers buried the ash layer in sediment, fossilizing the bones in near-perfect condition. Today, scientists excavate complete skeletons, rhinoceroses with jaws agape, young horses curled where they fell, able to reconstruct not only the species that lived here, but the sequence of their deaths. It is rare in paleontology to catch such a clear snapshot of disaster. Usually we work with fragments, guessing at causes. Here, the crime is written across hundreds of skeletons, each whispering the same diagnosis. The haunting question is not only how these creatures died, but how many more such episodes have vanished without record. Nebraska's fossil bed is unusual because conditions preserve the story so vividly. How many plains, forests, or valleys across the world once bore witness to similar distant ashfalls, only for the evidence to be scattered or erased? If one eruption could kill rhinos and camels 1,000 miles from its source, how many other quiet graveyards lie beneath our feet, their stories lost to erosion? In the end, the Nebraska fossils are not just a monument to ancient animals. They are a reminder that volcanic eruptions are never local, that their true footprint stretches across lives and landscapes we might never think to connect. And they challenge us with a sobering thought. If creatures as strong and resilient as rhinoceroses could be undone not by fire or impact, but by weeks of poisoned breath, what would it mean for us if such an ashfall were to descend again? What makes this fossil graveyard even more compelling is that it captures behaviour in motion, not simply biology frozen in stone. In several cases, paleontologists have uncovered mothers and juveniles side by side, their final moments intertwined. Young horses lie curled against larger adults, as if they sought comfort even as their bodies failed. The bones of turtles and cranes suggest that smaller animals lingered too, struggling in the same poisoned air. Unlike predators that might have picked off the weak, the ash offered no mercy. It smothered all equally, binding predator and prey into the same tragic tableau. The ashfall bed becomes less a random collection of bones and more a moment in time, a day, or perhaps a series of days, etched permanently into the earth. Geochemical analysis of the ash itself adds further detail. Under microscopes, its particles are jagged shards of volcanic glass, each one a splinter sharp enough to slice lung tissue at the microscopic scale. Unlike dust or pollen, these fragments do not dissolve or pass harmlessly. They lodge, irritate, and grind. With every breath, more damage accumulates. Laboratory comparisons with modern eruptions confirm the same process in living animals. During the eruption of Mount St. Helens in 1980, livestock downwind exhibited respiratory distress from inhaled ash. In Indonesia and the Philippines, farmers have reported cattle and goats weakened after volcanic falls. The Nebraska site, then, is not a mystery so much as a magnified lesson, a reminder that these silent drifting particles can become as deadly as lava when carried far enough. Another haunting element is the sheer duration of the deaths. Unlike sudden pyroclastic surges that kill in minutes, the inhalation of fine ash can stretch mortality into weeks. The bone growth associated with Marie's disease takes time, meaning these animals suffered through days of progressive weakness before collapsing. In that span, social herds likely tried to move, to migrate, perhaps even to outrun the haze. But the ash was everywhere, settling across the prairie, filling watering holes, coating plants. Every attempt to eat or drink only deepened exposure. To imagine those weeks is to realise that the tragedy was not one explosive moment, but a drawn-out unravelling of an entire ecosystem. Today, the ashfall fossil beds have been preserved as a state historic park with an active excavation site open to the public. Visitors can walk above the bones under a protective shelter, watching paleontologists uncover skeletons in the same positions they fell. It is a rare place where the violence of deep time is laid bare, not as abstraction, but as evidence at one's feet. For many who see it, the experience shifts volcanic eruptions from distant curiosities to tangible, immediate threats. This is not merely a chapter in the story of rhinos and camels. It is also a warning written in bone that distance offers no immunity, and that the air itself can become the most merciless killer of all. In the spring of 1815, a mountain in the Dutch East Indies tore itself apart. Tambora, on the island of Sumbawa, had rumbled ominously for days, but nothing could have prepared those nearby for the violence that followed. When the eruption came, it was not a polite plume or a single boom. It was a detonation so immense that sailors hundreds of miles away thought they were hearing cannon fire. Entire villages were buried under pyroclastic surges, harbours filled with floating pumice, and tens of thousands of lives were extinguished in an instant. Yet the most remarkable part of Tambora's story is that its deadliest effects unfolded far beyond Indonesia. The explosion of April 1815 threw so much material into the upper atmosphere that, for the next year, the whole planet became its shadow. The following summer, the year 1816, was unlike any other in recorded history. In New England, farmers awoke in June to find snow covering their crops. Frost struck again in July and August, killing corn before it ripened, leaving fields of withered stalks. Diaries from the time speak of families forced to slaughter livestock because there was no grain to feed them. People boiled weeds for food or left their farms entirely, heading westward in search of survival. Across the Atlantic, Europe fared no better. Cold rains and grey skies blighted the harvest. In Ireland, potatoes rotted in the ground. In Switzerland, famine sparked riots as bread prices soared. By winter, starvation had reached across continents, claiming lives not only from hunger, but also from diseases that preyed on weakened bodies. What had happened was a planetary experiment in forced climate change. Tambora's eruption injected an estimated 200 million tons of sulfur dioxide into the stratosphere. There, high above the weather systems we know, it combined with water to form a veil of sulfate aerosols, tiny droplets that reflected sunlight back into space. The result was a dimmer Earth. Temperatures dropped by as much as 3 degrees Celsius in the northern hemisphere. That may sound small, but agriculture balances on narrow margins. A few degrees meant frozen crops in June, shortened growing seasons and failed harvests across entire countries. The effects were cultural as well as biological. In Switzerland, a group of young writers trapped indoors by relentless rain spent their evenings telling ghost stories. From those sessions came Mary Shelley's Frankenstein and the first stirrings of modern science fiction. In China, famine drove migrations that altered regional demographics for generations. In India, food shortages helped spread a cholera pandemic. A single mountain's eruption rippled outward to shape literature, disease, and demography on a global scale. For scientists today, Tambora is a rare case study in how volcanic eruptions can shift climate in real time. Tree rings from North America and Europe show stunted growth in 1816, while ice cores in Greenland and Antarctica record the sulfur spike that marked the eruption's atmospheric fingerprint. These independent records confirm what diaries and newspapers described. The skies were dimmer, the earth was colder, and society felt the weight of a volcano half a world away. Tambora was not the largest eruption in Earth's history. It was not even a so-called super-eruption. Yet, it was large enough to remind us that the boundary between natural disaster and human catastrophe is thin. A volcano's immediate victims may number in the tens of thousands, but when the climate shifts, the circle of impact widens to millions. That is the lesson Tambora forced upon the 19th century. A single mountain can feed the hunger of the atmosphere, and the atmosphere can, in turn, starve continents. The haunting question left by Tambora is not whether such events will happen again. They will. But how prepared we are to face the shadows they cast. We cannot move farms out of the path of dimmed sunlight. We cannot relocate entire societies to warmer latitudes. All we can do is learn from the past, measure carefully, and recognise that when a volcano speaks with such force, it is not just a local conversation. It is a voice that carries across oceans, through skies, and into the very fabric of human survival. Part of what makes Tambora so unsettling is how invisible its weapon really was. Unlike a pyroclastic flow that carves scars into the earth, or lava that leaves behind hardened trails, the aerosols Tambora lofted into the stratosphere left no permanent mark on the land itself. They floated high above, beyond the reach of rain, drifting around the globe on currents that most people never notice. You could look up at the sky and see strange sunsets, painted with unusual crimson and violet hues, but you could not touch or smell the cause. Yet those suspended particles changed the fate of entire societies, more effectively than any invading army could. The enemy was not visible, but the losses were devastating. One of the more telling clues comes from art of the period. Painters in Europe began depicting sunsets that were strangely lurid, skies smeared with copper and blood-red bands. For a long time, art historians debated whether this was symbolism or style. Only recently did atmospheric scientists match those depictions with what we know about volcanic aerosols. The colours were not artistic invention. They were the world as it really looked beneath Tambora's volcanic veil. The skies themselves became part of the archive, preserved not just in ice cores and tree rings, but on canvas. Economic consequences were just as dramatic as the cultural ones. In New England, the crop failures of 1816 caused waves of migration into the American Midwest. Families who could no longer farm rocky soils in Vermont or Maine packed up and headed west, looking for land where a late frost might not mean starvation. Some historians argue that Tambora accelerated the settlement of regions like Ohio and Indiana, not because of political policy, but because of cold weather that pushed people outward. In Europe, grain prices doubled in some cities, fueling unrest that mingled with the political aftershocks of the Napoleonic Wars. It was a reminder that volcanic eruptions can act as silent political players, shifting populations and igniting crises that have nothing to do with lava. The story also contains lessons about resilience and improvisation. In parts of Switzerland, peasants tried to harvest wild plants usually ignored as food. In North America, some communities relied on fish from rivers and lakes to replace failed grain harvests. None of these solutions erased the suffering, but they do show how humans adapt, even clumsily, to sudden environmental shocks. That said, adaptation had limits. Cholera spread in part because weakened populations were more vulnerable, and because mass movement of people facilitated transmission. What began as a volcanic eruption in the tropics cascaded into a pandemic that would ripple through the 19th century. When scientists today model what a large eruption might do to modern societies, Tambora is their baseline case study. With satellites, we now track aerosol layers circling the globe after even small eruptions. In the early 1990s, Mount Pinatubo in the Philippines released about 1/10 of Tambora's sulfur dioxide, and global temperatures still dipped by nearly 0.5 degrees Celsius. The pattern matched Tambora's legacy on a smaller scale, giving confidence that our reconstructions of the past are accurate. If Pinatubo cooled the planet for 2 years, then Tambora's 3-degree plunge in 1816 becomes more than plausible. It becomes expected. This perspective also forces us to ask uncomfortable questions. If a single eruption 2 centuries ago could upend agriculture and public health across multiple continents, what would happen to our modern, globally interconnected food system under the same strain? In 1816, famine was local and regional. Today, supply chains stretch across oceans, populations are denser, and billions depend on crops vulnerable to even small disruptions. Tambora shows us that the link between volcano and dinner plate is shorter than we might like to imagine. The eerie part is how quickly the world recovered once the aerosols settled out. By 1817, the skies cleared and crops returned. But for those who lived through that single year, the memory lingered. Newspapers called it the miserable year. Farmers spoke of a poverty year. Writers remembered the year without a summer. It did not last long, but it lasted long enough to shape migration patterns, literature and demographics. That is the paradox of volcanic climate disasters. They can be both temporary and transformative, leaving marks in culture and history that endure long after the physical traces have vanished. And so, Tambora stands as a reminder that when a mountain speaks loudly enough, the entire world must listen, even if the voice is only a whisper of ash and gas high in the stratosphere. Its lesson is humbling. Catastrophe need not arrive with fire at your doorstep. Sometimes it arrives with a chill in June, a failed harvest, or a crimson sky that no one can explain. The haunting question left to us is simple. If this was the toll from a single eruption just over 200 years ago, what might we face if the Earth chose to repeat the lesson at an even greater scale? 74,000 years ago on the island of Sumatra, the Earth exhaled with a violence almost beyond comprehension. The Toba eruption ranks among the largest known in the entire Quaternary period, ejecting thousands of cubic kilometres of material into the skies. The scale was so vast that Lake Toba, one of the largest volcanic lakes on the planet, still fills the sky today. But what makes Toba infamous is not merely the size of its crater. It is the enduring question of what happened to our own species in its shadow. Did a single eruption nearly erase Homo sapiens from the Earth? Or have we exaggerated its reach, confusing drama with certainty? Evidence from geology paints a picture of planetary disruption. Ash from Toba has been found across the Indian Ocean basin, in deposits stretching from Malaysia to the Arabian Sea. In some places, the layer is several meters thick, smothering ancient landscapes in grey. The eruption is believed to have expelled enough sulfur dioxide to veil the planet in aerosols, similar to Tambora but multiplied many times over. Models suggest global temperatures may have dropped sharply, perhaps by several degrees, for years. Crops did not exist then, but ecosystems still depended on photosynthesis, and a dimmed sun would have meant stressed vegetation, dying herds, and a chain of hunger rippling through every level of the food web. The human story is written less clearly. Geneticists studying our DNA once argued that humanity carries the signature of a bottleneck, a sharp reduction in population size around this time. Some estimates suggested only a few thousand individuals survived, clustered in isolated refuges while much of the world became hostile. The idea gained dramatic weight because it fit so neatly with the eruption of Toba. A supervolcano had exploded. Our ancestors nearly vanished. It was a tidy, terrifying story, but science rarely stays tidy for long. Archaeology complicates the picture. Sites in southern Africa show evidence of continuous human occupation across this period, with stone tools and hearths appearing unbroken through the supposed bottleneck years. In India, excavations beneath and above the Toba ash layer reveal that people were present before the eruption and continued living there afterward. Their tools do not show a sudden collapse or cultural disruption. It seems that some groups weathered the eruption with resilience, even under skies likely dimmed by ash. The The supposed near extinction of humanity may not have been global, but more regional, affecting some populations harshly while sparing others. Still, there is little doubt that the eruption stressed the species. Surviving in small groups along coasts or in refuges with stable resources, our ancestors would have faced not only scarcity but isolation. In genetic terms, bottlenecks are dangerous because they limit diversity. Reduced diversity means less ability to adapt to future challenges, whether environmental or disease. If humanity truly passed through such a narrow corridor of survival, it left us both vulnerable and strangely unified, our genomes carrying the echo of that near miss. The debate today continues. Was the bottleneck real, exaggerated, or an artifact of other processes? We do not yet know for certain. The importance of Toba lies less in a definitive answer and more in the humility it forces. Here is a natural event so powerful that it became tangled with the fate of our species. It reminds us that our survival has not always been inevitable. We are not only shaped by culture and ingenuity, but also by the moods of the earth beneath us. For those living then, the eruption must have felt like the end of the world. Grey skies, dying animals, dwindling plants, a silence broken only by the crack of distant thunder or the hiss of falling ash. That their descendants eventually invented art, agriculture and cities is a testament not to invincibility, but to persistence in the face of unimaginable odds. And so, Toba's lesson remains unresolved yet enduring. Did it nearly wipe us out, leaving just a few small bands clinging to survival? Or did it bruise us deeply without breaking us, a scar rather than an amputation? Either way, it shows that the line between continuity and collapse is thinner than we like to believe. The haunting question lingers. If a single eruption could leave such uncertainty in our very DNA, how many other times has nature's breath carried us to the brink without our even knowing? The legacy of Toba is not confined to ash layers or genetic charts. It also lives in the way scientists across disciplines wrestle with uncertainty. Volcanologists, geneticists and archaeologists each approach the question from different directions, and the results do not always align neatly. This mismatch is instructive because it forces us to think about the limits of our tools. DNA can preserve echoes of ancient stress, but cannot tell us whether it was caused solely by an eruption, by climate shifts, or by the complex pressures of small populations scattered across continents. Ash deposits can reveal how far material spread, yet they cannot reveal what it felt like to breathe, hunt, or give birth under skies veiled in sulphur. Archaeology, for its part, leaves a fragmentary record of stones and bones that may or may not represent the whole picture of survival. Each piece is partial, and the challenge is fitting them together without forcing them into a single dramatic narrative. One intriguing line of evidence comes not from Africa or India, but from the seas. Marine sediments hold tiny fossils of plankton that responded to Toba's fallout. Changes in their chemistry suggest disruptions in ocean productivity and circulation. If oceans dimmed or cooled even briefly, this could have rippled through global climate in ways that remain hard to model. Such clues hint that the impact may have been broader than once assumed, even if humanity proved more resilient than the stark bottleneck story allowed. In other words, Toba's punch landed hard on the Earth system, even if it did not quite knock our species unconscious. Another dimension is cultural. Some researchers wonder whether the shared myths of fire, darkness and survival, found in widely separated traditions, might faintly echo real disasters such as Toba. While this remains speculation, it reminds us that humans have always encoded catastrophe in story. Even if no tale from 74,000 years ago can be traced directly to that eruption, the instinct to make meaning from ash and fear has been with us for as long as language itself. The possibility that our ancestors not only endured but also remembered in some way reinforces the idea that survival is more than biology. It is also narrative. The debate over Toba's consequences has also reshaped how we think about risk today. For decades, the bottleneck hypothesis was invoked as a warning. If one volcano nearly ended us once, another could do so again. Even as that view has softened, the underlying caution remains. Super-eruptions are rare, but they are not imaginary. They sit on the boundary of events that feel too big to fit into human timescales, yet have already happened in ours. That knowledge alone is sobering. It challenges us to prepare not because we expect Yellowstone or another giant caldera to erupt tomorrow, but because we know the Earth does not measure time in the same units we do. Ultimately, Tober's dark lesson is not about extinction but fragility. It shows how quickly circumstances can shift, how survival can depend on luck of location, access to resources, or sheer chance. If small bands in Africa, South Asia, and perhaps coastal refuges endured while others perished, then our existence is built on their improbable persistence. That thought can be both unsettling and strangely comforting. Unsettling, because it highlights how thin the thread of continuity really is. Comforting, because it demonstrates that resilience is also woven deeply into our lineage. And so the haunting question remains open. Did Tober nearly wipe us out? Or did it simply remind us of our vulnerability? We may never know in absolute terms, but perhaps the more important truth is that our species has lived through the kind of disaster that reshapes continents, skies, and oceans. To stand here now is to carry that survival quietly within us. Whether it was a bottleneck or a bruise, Tober whispers across millennia the same reminder. The Earth does not need our permission to change the rules, and survival is never guaranteed. That awareness may be the truest inheritance left by a volcano that once dimmed the sun. How do you X-ray a living volcano? Unlike broken bones or diseased lungs, you cannot simply slide a mountain into a hospital machine and wait for a glowing image to appear. Volcanoes are not cooperative patients. They shift, crack, rumble, and seethe in ways that resist direct observation. In the late 20th century, as scientists grew increasingly aware that Yellowstone was not a relic, but an active system, they faced the riddle of how to see into the crust. The tools they turned to were seismic waves, ripples of energy generated by earthquakes both large and small, which move through the Earth and change speed and direction, depending on the materials they pass through. In essence, seismology became the world's most powerful X-ray, capable of turning the opaque ground beneath Yellowstone into a three-dimensional image. The technique is called seismic tomography. Just as medical tomography takes many two-dimensional X-rays to reconstruct the full shape of an organ, seismic tomography collects waveforms from thousands of tremors, both local quakes and distant global ones. By measuring how long each wave takes to reach an array of seismometers, and by noticing subtle delays or accelerations, scientists can infer whether the waves pass through solid rock, fractured zones, or pockets of melt. The process is not quick. It involves years of recording, painstaking computer modelling, and repeated adjustments. By the 1990s, researchers had gathered enough data from Yellowstone and its surrounding ranges to begin assembling the first coherent pictures of what lay below the famous geysers and hot springs. What they saw was startling. Rather than a narrow cylinder or small chamber, the upper crust beneath Yellowstone appeared as a vast pancake-like body of partly molten rock. Scientists described it memorably as a frying pan, shallow in depth, but stretching across tens of miles, with a handle protruding to the northeast. This analogy stuck not because it was folksy, but because it captured the surprising geometry. A thin but broad reservoir, lying roughly 3 to 9 miles beneath the surface, much wider than it was deep. The handle represented an extension of the chamber, feeding into areas beyond the main caldera. This picture overturned earlier assumptions that Yellowstone's magma might be stored in a relatively compact pod. Instead, it seemed to spread laterally in a sheet-like body, more like a swollen blister than a narrow pipe. Estimating how much of this body was truly molten became the next challenge. Seismic data cannot give a direct percentage, but it can indicate zones of slower wave travel, consistent with melt interspersed within solid rock. The results suggested that only a fraction, perhaps 5 to 15%, was liquid magma at any given time, with the rest being hot but rigid crystalline material. This distinction matters because a reservoir that is mostly solid does not behave like a giant vat of lava waiting to burst. It is more like a sponge saturated with heat and pockets of fluid. The revelation was sobering in its own way, because it meant that eruptions could be fed by relatively small changes in melt percentage. A slight increase in heat or influx of new magma could alter the system's dynamics dramatically, even if the majority of the chamber remained crystalline. The mapping of the frying pan chamber also explained surface phenomena that had puzzled observers for decades. The caldera floor had been seen to rise and fall like a slow-moving piston, with parts of the park uplifting several inches over years before subsiding again. Now it was clear that these pulses reflected pressure changes within the sprawling chamber. When melt or hot fluids accumulated, the ground swelled. When they drained or cooled, the ground settled. The crust above Yellowstone, in other words, was flexible, able to bend and flex under the breathing of the magma below. This realization underscored just how alive the system was. The landscape tourists drove across, photographed and picnicked upon was not fixed. It was a skin stretched over a restless body. The advances of the 1990s and early 2000s came from both technological improvements and academic persistence. Faster computers allowed more complex models of seismic wave travel. Expanding seismic networks provided finer resolution, with dozens of instruments spread across the park rather than just a handful. Collaborations between the University of Utah, the United States Geological Survey, and the Yellowstone Volcano Observatory pooled expertise and resources, enabling long-term monitoring instead of one-time studies. Each new quake, whether a tiny microtremor or a moderate jolt felt by visitors, became another probe through the crust, another line of data added to the grand reconstruction. The implications for hazard assessment were significant. For the first time, scientists could point to a real mapped body of the magma beneath Yellowstone and describe its shape and partial melt content. The frying pan analogy entered not only scientific literature but also public awareness, often simplified or exaggerated in popular accounts. While researchers emphasized that such a chamber was normal for an active caldera and did not mean an eruption was imminent, the very existence of a mapped magma body captured imaginations. For those who had long dismissed Yellowstone as little more than a geothermal curiosity, the tomography results forced a re-evaluation. The geysers and hot springs were not surface oddities. They were visible symptoms of a vast underground system. What seismic tomography also revealed, however, was the limitation of human vision. The images produced were fuzzy, more like impressionist paintings than crisp photographs. Resolution depended on earthquake distribution, and gaps in the network left blind spots. Scientists stressed that their models were best approximations, not literal pictures. Yet even with these caveats, the work marked a breakthrough. For the first time, the hidden architecture of Yellowstone's shallow magma system had been drawn in broad strokes. It was less a complete answer than an opening window, offering a glimpse of the restless forces shaping the park. The haunting question that emerged from this era was simple. If we can now see the frying pan, how well do we truly understand what it might do? The chamber's presence explains uplift, hot water circulation, and geothermal activity. But whether those same processes are harbingers of future eruptions or just the ordinary breathing of a living system remains uncertain. Imaging the patient is one thing. Predicting its future health is another. And Yellowstone, as scientists discovered, is a patient that always keeps part of its story hidden from view. Where was all the extra carbon dioxide coming from? For years, geologists monitoring Yellowstone puzzled over a mismatch. The gases venting from its geysers and steaming pools were more abundant than the shallow magma chamber alone could explain. Instruments recorded fluxes of carbon dioxide that seemed to suggest a deeper and more voluminous source. Yet for decades, the model stopped at the upper chamber, the frying pan-shaped body identified in the 1990s. If that chamber contained only a few percent molten rock, where was the surplus gas being generated? The question lingered as a quiet inconsistency, one of those nagging anomalies that refused to go away. In 2015, a group of researchers led by scientists at the University of Utah unveiled a new study in science that reframed the puzzle. Using an innovative combination of seismic tomography techniques, they imaged a much deeper magma reservoir beneath Yellowstone's known chamber. This was not a modest addition, but a vast reservoir, 4 times larger than the shallow body above. The missing source of carbon dioxide had finally been located, a lower crustal reservoir, 12 to 28 miles beneath the surface, acting as the giant supplier for the restless system above. The discovery did not come from a single stroke of luck, but from years of integrating data. The team combined information from local seismic networks which are sensitive to shallow crustal structures with records from EarthScope, a continental-scale array of seismometers capable of imaging much deeper. By merging these two datasets, the researchers produced the most detailed picture yet of Yellowstone's magmatic plumbing. Instead of a simple upper chamber perched on top of a plume, they revealed a continuous system, a mantle hotspot feeding into a deep reservoir which in turn supplies the upper chamber. For the first time, the volcanic anatomy could be traced as a coherent whole, from plume to chamber. The deeper reservoir was not a molten lake. Like the shallower frying pan above, it was mostly solid rock with scattered melt pockets. Estimates suggested only about 2% of it was liquid, but the scale was staggering, roughly 11,000 cubic miles in volume, enough hot rock to fill the Grand Canyon more than 11 times over. Even at such a low melt percentage, the absolute quantity of liquid magma dispersed through that volume was immense, and importantly, it offered a source for the excess carbon dioxide. Degassing from such a reservoir could easily account for the fluxes measured at Yellowstone's surface, solving a mystery that had nagged for years. Scientists emphasized that the discovery did not mean Yellowstone's hazard level had suddenly changed. The system had always been this size. It was only our image of it that expanded. The hazard is the same, one of the researchers noted at the time. We just understand it better now. Still, the finding captured global attention. Headlines blared about a magma body big enough to fill multiple Grand Canyons. For the public, it fed apocalyptic imaginings. For scientists, it represented progress, a clearer sense of scale, a more accurate map of the pathways by which heat and gas move through the crust. The existence of a deep reservoir also clarified the role Yellowstone plays in the larger geological system of North America. Supervolcanoes are not surface curiosities but long-lived conduits for mantle material. The discovery illustrated how material rising from at least 40 miles deep in the earth does not move directly to the surface in one leap. Instead, it pools, fractionates, and accumulates in stages. The lower reservoir acts as a staging ground, where hot rock partly melts, volatiles are released, and chemical differentiation occurs. From there, batches of melt can migrate upward into the upper chamber, where they may eventually erupt. This layered structure is consistent with other large volcanic provinces, reinforcing the idea that Yellowstone is not unique in form, only in scale and visibility. One of the more subtle insights from the 2015 study was that the deep reservoir explained long-standing questions about gas chemistry at Yellowstone. For decades, scientists had measured isotopic signatures in carbon dioxide that hinted at a deeper mantle connection. The gases were not purely crustal in origin. With the identification of the reservoir, those signatures made sense. The plumbing system, it turned out, extended further down, directly linking surface emissions with mantle-derived materials. In practical terms, every breath of steam drifting across Yellowstone's geyser basins carries with it a chemical fingerprint of Earth's interior, exhaled from reservoirs miles beneath the crust. The discovery also underscored the humility required in studying systems of such scale. For more than half a century, researchers had thought the upper chamber was the main story. Then, with better imaging, a reservoir 4 times larger appeared below it, a reminder that even with dense networks and powerful computers, our view of the Earth remains partial. If a body that large could remain hidden until recently, what else might lie beneath, beyond the limits of resolution? The haunting implication is that geology often reveals itself only in fragments, leaving us to piece together vast systems with the patience of detectives. It is tempting to imagine the deep reservoir as a threat waiting to rise, but the science points to a more nuanced picture. Its discovery does not forecast catastrophe. It shows continuity, a hotspot plume, a deep staging chamber, a shallow frying pan, and surface hydrothermal features all linked in one flow of heat and gas. What Yellowstone gave us in 2015 was not a countdown clock, but a fuller diagram of the machine. The question that lingers is whether such knowledge makes us safer, or simply more aware of how little control we have. We now know where the carbon dioxide comes from. Whether we have learned what truly matters, that is still an open debate. One underappreciated aspect of the 2015 discovery is how it reshaped Yellowstone's role as a natural laboratory. Before this study, Researchers often frame the park's hydrothermal features as windows into the shallow crust. Afterward, the emphasis shifted toward Yellowstone as a complete system, extending from the mantle to the boardwalks. This broader view allows comparisons with volcanic provinces across the globe. Iceland, for instance, sits atop a mantle plume and shows a layered reservoir system not unlike Yellowstone's, though in a different tectonic setting. Hawaii, too, demonstrates deep magma storage feeding upper chambers. By connecting Yellowstone to these global analogues, scientists began to see it less as a one-off oddity and more as a particularly accessible example of deep Earth processes that occur in many places. The discovery also forced refinements in hazard modelling. While it did not raise the probability of eruption, it did complicate the pathways by which eruptions might develop. Melt rising from the lower reservoir does not necessarily travel in a straight line. Instead, it can stall, freeze, or react chemically with surrounding rock. This creates a variety of scenarios for how eruptions might initiate. Some models suggest that injections from the deep reservoir could destabilize parts of the upper chamber, triggering smaller, localized eruptions rather than continent-spanning blasts. Others emphasize the role of volatiles. Carbon dioxide and water released from the deep reservoir could migrate upward, pressurizing the shallow system and altering its behavior. Each of these possibilities is speculative, but the point is that the deep reservoir added new complexity to the conversation. Perhaps most striking is what the deep reservoir tells us about time. The chamber's immense volume combined with its relatively low melt fraction means it evolves slowly. Processes of melt accumulation, volatile release, and chemical differentiation may unfold over tens of thousands of years. To glimpse such a structure is to confront the mismatch between human lifespans and geological rhythms. The very act of mapping it collapses those timescales into a moment of human comprehension. But the reservoir itself will continue shifting long after we are gone. In that sense, the 2015 study did more than solve a carbon puzzle. It reminded us that Yellowstone's story cannot be reduced to a human calendar. And yet, even with such sobering scale, the discovery holds practical relevance. Understanding where gases originate helps refine monitoring strategies. For example, distinguishing between carbon dioxide sourced from the shallow frying pan versus the deeper reservoir allows scientists to interpret changes in emissions more accurately. A sudden spike might mean different things depending on its chemical fingerprint. By tracing gases back to their point of release, researchers can begin to untangle whether surface signals represent shallow adjustments or deeper stirring. This kind of nuance is essential for credible hazard communication, where the difference between background activity and genuine warning may hinge on subtle chemical clues. Ultimately, the missing carbon mystery illustrates the quiet power of science to peel back layers of uncertainty. It did not deliver apocalyptic headlines in the sense of imminent doom, but it deepened our understanding of a system whose scale dwarfs us. The haunting question left behind is not whether the reservoir will erupt tomorrow, but whether we can continue to refine our tools fast enough to keep pace with a planet that always seems one layer deeper. What does it mean when a lake tilts? Most of us assume that shorelines are fixed, that water finds its level and remains there, unmoved by anything but the wind. Yet at Yellowstone, even the shape of a lake can betray the restlessness beneath. Beginning in the 1970s, geophysicist Bob Smith and his colleagues began to document puzzling shifts around Yellowstone Lake. Using careful surveying techniques, they noticed that certain shorelines had risen relative to others. Villages once perched neatly at water's edge were now stranded inland, their archaeological remnants high above the lapping waves. Elsewhere, areas once habitable had slipped below the surface. The lake itself had not changed. The ground had. The realization that the caldera floor was not static but rising and falling unsettled assumptions. Yellowstone was not a dormant landscape occasionally decorated by geysers. It was alive, breathing in cycles of uplift and subsidence that could tilt entire basins. In the 1970s, surveys showed areas of the caldera floor rising by as much as 7 inches a year. Over the span of a decade, this added up to feet of motion. For any geologist trained to think of rock as rigid and immovable, the numbers were astonishing. Something beneath the surface was inflating the crust like a mattress, and then letting it deflate again. Native American sites around Yellowstone Lake added a deeper timescale to the story. Archaeologists had long documented shifting village remains that did not align with stable water levels. Fire pits, tools, and bones appeared in places that only made sense if the ground itself had moved over centuries. Shorelines that once cradled human life had later sunk underwater, preserving artifacts beneath the layers of silt. The record revealed that cycles of uplift and subsidence were not just modern quirks but ancient rhythms, ongoing for millennia. Yellowstone's people had unknowingly lived upon a moving platform, adjusting their settlements without ever seeing the cause. The scientific task became to measure these changes with precision. By the 1980s and 1990s, improved surveying equipment and later GPS technology allowed geologists to track ground movement in centimetres rather than feet. Networks of monitoring stations dotted the park, recording each subtle heave and dip. What emerged was a pattern: decades of uplift, sometimes rapid, followed by intervals of subsidence. At times the floor of the caldera rose by nearly 3 feet before slowly settling back. These motions were not catastrophic but slow and steady, imperceptible to visitors yet undeniable to instruments. Explanations focused on the shallow magma chamber, identified through seismic tomography. Pressure fluctuations in this partly molten body could account for the inflation and deflation of the crust above. When magma or hot fluids accumulated, the ground swelled. When they drained or cooled, the surface sagged. Yellowstone in this view was less like a solid block of rock and more like a diaphragm, expanding and contracting with pulses from below. The lake tilting was simply the most visible manifestation of a deeper breath. But the metaphor of breathing should not lull us into complacency. For a volcano, such motions are ambiguous. They can occur without eruption, reflecting nothing more than the normal circulation of heat and fluids. Yet in other settings, uplift has preceded eruptions, a sign of pressure building toward release. The challenge lies in interpretation. Was Yellowstone's uplift a rehearsal, a release valve, or something in between? The cycles documented by Smith and later teams provided no clear answers. They simply confirmed that the caldera was never still. These findings also reframed the archaeological record in a humbling way. Native peoples had long known Yellowstone as a place of dynamic power. Oral traditions often emphasized the danger of venturing too close to steaming pools or unstable ground. The shifting lake shorelines added another layer of experience, one recorded not in words but in the placement of hearths and tools. When villages disappeared beneath rising waters, survivors likely rebuilt higher up without knowing that the cause lay miles beneath their feet. Science has only recently supplied the mechanism, but the experience of living on moving ground is as old as human presence in the park. One of the most remarkable features of Yellowstone's uplift story is its scale. These are not local landslides or surface deformations caused by weather. The entire floor of a 40 by 25 mile caldera has the capacity to lift like a slow tide, altering landscapes over decades. To grasp this is to realize that humans, animals, and forests occupy what is essentially a restless platform, an arena that rises and falls according to forces we cannot see. Yellowstone is not scenery, it is process. By the early 2000s, continuous GPS networks made it possible to watch this process in near real time. Data streams showed the caldera floor pulsing with surprising vigor, sometimes shifting by several inches in a single year. Scientists watched these graphs with both fascination and unease. Each line represented Earth's hidden motions translated into digital records. The challenge was not seeing the movement, but interpreting its meaning. Was the ground preparing for something extraordinary, or was it merely breathing as it had for hundreds of thousands of years? The haunting question remains unresolved. When a lake tilts and a valley rises, are we witnessing precursors to catastrophe, or the ordinary size of a living caldera? The evidence tells us only that Yellowstone moves, sometimes dramatically, always mysteriously. To live in its shadow is to accept that even the ground beneath our feet may not be fixed. It shifts with a rhythm we can measure but not fully understand, a rhythm that has carried on long before us and will continue long after. What sound does magma make as it rises? To most of us, volcanoes are silent until they erupt, roaring only when gas explodes, ash clouds billow, or lava fountains crackle. Yet in the decades before such displays, the Earth is never truly quiet. Deep underground, magma moving through cracks, forcing its way upward, generates a distinct seismic signature known as harmonic tremor. Unlike ordinary earthquakes, which arrive as sharp jolts, harmonic tremor is continuous, resonant, and strangely musical. It is as if the crust itself were vibrating like the body of a cello, amplifying the movement of molten rock into a low, steady hum. The first time scientists truly recognized harmonic tremor as magma's fingerprint was not at Yellowstone but at other restless volcanoes around the world. In the mid-20th century, eruptions in Alaska, Iceland, and Central America showed a repeating pattern. Before lava breached the surface, seismometers recorded a sustained oscillation, sometimes lasting hours or days. It was not noise in the system, nor random coincidence. This was magma squeezing upward, fracturing rock, pressurizing conduits, and creating vibrations that instruments captured as eerie waves. The term harmonic came from the way these signals resembled sound harmonics, overtones produced by vibrating strings or air columns. Earth itself in these moments seemed to be singing. At Mount St. Helens in 1980, harmonic tremor became infamous. As magma pushed into the mountain, seismometers recorded extended episodes of low-frequency rumbling. Shortly thereafter, the catastrophic lateral blast tore away the mountain's north flank. Later analysis confirmed what volcanologists now take as a fundamental truth. Harmonic tremor is one of the clearest indications that magma is not simply stored, but on the move. Not every tremor leads to eruption, but every eruption seems to leave behind its tremors. Scientifically, the mechanics are subtle. Magma contains gases, carbon dioxide, sulfur dioxide, water vapor, that expand as pressure decreases toward the surface. When these gases bubble and pulse within molten rock moving through conduits, they set the surrounding walls vibrating. Picture a pipe organ filled not with air but with viscous melt. The sound does not reach human ears, but seismometers pick it up readily, translating vibrations into jagged lines across recording paper or digital graphs. The frequency of these waves often falls within a narrow band, different from the wide spectrum of ordinary earthquakes. It is this consistent pitch, this unnatural steadiness, that alerts volcanologists to magma's presence. For scientists at Yellowstone and elsewhere, harmonic tremor is both a gift and a warning. It provides rare evidence of magma in motion, a process otherwise invisible. Yet it also carries ambiguity. Not every tremor ends in eruption, and distinguishing between harmless intrusions and dangerous ones remains difficult. At Kilauea, in Hawaii for example, harmonic tremor can accompany small lava outpourings that barely disrupt daily life. At more explosive volcanoes like Mount Pinatubo or Nevado del Ruiz, similar signals have preceded catastrophic events. The context, chemistry, and gas content matter as much as the tremor itself. Listening to the Earth in this way has required not only technology but imagination. Early seismologists described harmonic tremor almost poetically, noting its resemblance to the drone of an organ or the hum of distant machinery. Even today, some researchers convert seismic data into audible sound, creating recordings where one can literally hear magma moving. The results are unsettling, a low rumbling note that wavers and builds like the breath of some hidden giant. For teaching and public outreach, these audio renderings convey what graphs alone cannot: the visceral sense that the planet is alive, murmuring beneath us. At Yellowstone, harmonic tremor has been detected at times, though never in a pattern that suggested imminent eruption. The park's seismometers are sensitive enough to capture even faint signals, and part of the monitoring effort is to listen constantly for these peculiar vibrations. When they occur, scientists examine them carefully, comparing them with other data on gas flux, ground deformation, and seismic swarms. Alone, a tremor is intriguing. Combined with other anomalies, it can raise concern. The challenge is never to treat it as a solitary oracle, but as one clue in a complex symphony of signs. The eerie beauty of harmonic tremor lies in what it symbolizes. It is the volcano speaking in its own language, a language we have only recently learned to translate. It tells us that magma is restless, that the plumbing is active, that forces beneath the crust are not static. Yet it does not tell us when or how those forces will break through. To listen to tremor is to eavesdrop on a conversation we are not fully equipped to understand, and so the haunting question lingers. If a volcano sings before it erupts, can we ever learn to hear the final verse in time? Scientists remain cautious. Harmonic tremor warns us that movement is happening, but it is not prophecy. Like a heartbeat that quickens without warning, it can fade or escalate unpredictably. Still, the fact that we can even hear it at all is remarkable. The Earth gives us whispers of its intentions, low and resonant, waiting for us to listen. Whether we interpret them correctly is another matter, one that may determine whether we are ready when the next eruption comes. One of the more surprising places harmonic tremor has proven valuable is beneath the ocean. On the flanks of mid-ocean ridges, where volcanic activity is hidden under thousands of feet of seawater, traditional observation is impossible. Seismometers on the seafloor have recorded long, steady tremor signals that revealed eruptions otherwise invisible. In some cases, the first evidence of a submarine lava flow was not a plume of ash or a column of steam, but a peculiar rhythmic vibration travelling through the crust. These discoveries underscored the universality of magma's song. Whether beneath forests, glaciers, or the abyssal plain, rising melt leaves behind a seismic melody that cannot be faked by storms, landslides, or tectonic shifts. In Iceland, where ice caps bury several active volcanoes, harmonic tremor has served as one of the only early warning signs of subglacial eruptions. As magma melts through ice, the overlying glacier muffles sound and sight, but seismometers catch the tremor long before water floods outward. During the eruption of Grimsvötn in 2011, harmonic tremor spiked dramatically before ash pierced the ice. Here, the steady vibration was not just an academic curiosity, but a practical alarm, allowing airspace to be closed and lives to be protected. The study of tremor has also expanded into physics laboratories, where researchers attempt to replicate the process in miniature. By pumping fluids through pressurized rock samples, scientists can watch how bubbles, fractures, and flow regimes create vibrations. Some experiments suggest that harmonic tremor arises not only from gas pulsing, but also from the resonance of cracks themselves, like flutes carved into the crust. Each crack has its own frequency, and when magma flows through, it excites those natural pitches. What emerges on a seismogram is not random noise, but the combined chorus of many resonating fractures, each playing its part in the subterranean orchestra. These insights remind us that harmonic tremor is not a single sound, but a family of related signals. Some are high-pitched, short-lived chirps, others are deep booming notes that last for days. Distinguishing between them is a growing field, one that blends geology, acoustics, and even music theory. The parallels are more than metaphorical. Analysing tremor often involves the same mathematical tools used to study harmonics in musical instruments. The Earth, in effect, is a reluctant musician, producing tones as magma pushes its way upward. For the public, the eerie allure of harmonic tremor lies in the thought that a volcano hums before it explodes. For scientists, the allure is more pragmatic. Each tremor may be a clue about depth, gas content, or the size of a magma intrusion. But in both cases, the lesson is the same. The planet does not move in silence. It gives off signals, often faint and easy to miss, but unmistakable once trained ears, or instruments, are listening. The haunting question remains whether harmonic tremor will ever allow precise forecasts. It may be that these notes, while distinctive, are too ambiguous to serve as a countdown. Or it may be that with better networks and deeper analysis, tremor will someday become the most reliable alarm we have. Until then, scientists continue to listen, knowing that when the Earth begins to hum, it is telling us that something beneath is stirring. Would we even know before Yellowstone blew? The internet is full of quick answers, usually accompanied by shaky phone footage and ominous music. But the truth, as usual, is more patient. Volcanoes, even those that have not erupted for hundreds of thousands of years, do not leap from dormancy to catastrophe in a single day. They stir, they grumble, and they give off clues, if we know how to read them. The challenge is not the absence of warning, but our ability to interpret it with humility, separating science from panic. The first sign would almost certainly be ground movement. Yellowstone breathes. The caldera floor has risen and fallen by meters in the past century, without any eruption to follow. Tilt meters and GPS stations are scattered across the park to watch for these shifts. A sudden acceleration in uplift, say 10 centimeters in a matter of weeks rather than years, would set off alarms. Imagine a city the size of Houston quietly swelling upward, not from construction but from magma pushing gently against the crust. That kind of inflation cannot be hidden. Satellites would see it, instruments would log it, and scientists would have no trouble confirming it. Alongside uplift would come earthquakes. Yellowstone already has thousands each year, most too small for visitors to notice. These are background noise caused by faults adjusting and water circulating through hot rock. What would worry seismologists is not a single large quake, but swarms, hundreds of small tremors clustering in space and time, migrating upward like footsteps traced through the crust. Such swarms have happened before without eruption, but if they coincided with rapid uplift, the concern would deepen. It is a little like listening to a basement creak in the night. One creak is nothing. A whole staircase groaning in sequence suggests someone is walking up. If uplift and swarms are the footsteps, then gas is the breath. Yellowstone exhales carbon dioxide and sulfur dioxide through its geysers and fumaroles, releasing tens of thousands of tons daily. These levels are measured with spectrometers and air sensors. A sharp spike in gas flux, especially sulfur dioxide, would suggest that fresh magma had risen close enough to release its volatiles into the surface system. The chemistry of those gases matters too. Ratios between carbon dioxide and sulfur dioxide can indicate whether magma is shallow or still deep. To volcanologists, a plume is not just steam, it is a coded message about what lies below. Overlaying all of these signals is the sound of harmonic tremor, the low hum of magma in motion. Unlike ordinary earthquakes, which crack rock and then fall silent, harmonic tremor continues, a vibration that builds and sustains. If it began rumbling across multiple stations lasting hours instead of seconds, scientists would know that magma was no longer content to sit quietly. It would be moving into open conduits, resonating through cracks, and announcing its intent. Taken together, these four threads, uplift, swarms, gases, tremor, form the outline of what we would actually see. They would not appear overnight. They would unfold over weeks to months, possibly even longer. The question is not whether we would notice, but how we would respond. Geological time feels slow to us, but in crisis it can feel uncomfortably fast. 100,000 years between eruptions is security. 100 days of escalating warning signs is not. This is where myths often distort the conversation. Viral videos claim that animals stampeding or tourists feeling sulfur smells are the first and only signals. But in reality, no eruption of this scale could sneak up unannounced. The sheer volume of magma required means long preparation. When Mount Pinatubo erupted in 1991, weeks of tremors and swelling allowed tens of thousands of people to be evacuated. When Mount St. Helens reawakened in 1980, scientists had months of bulging and seismic activity to monitor. These were comparatively small eruptions, yet they still gave time. A system as massive as Yellowstone would almost certainly provide warning on a scale visible not just to scientists but to the entire public. The haunting question, then, is not would we know, but would we listen? We live in a world saturated with data and mistrust. Scientists at the Yellowstone Volcano Observatory already publish regular updates, often clarifying that nothing unusual is happening. Yet those reports rarely spread as fast as a dramatic YouTube clip or a tweet claiming the park is about to explode. If the true signs did appear, they might drown in the same sea of speculation. And here lies the uncomfortable irony. The Earth would speak clearly enough, but our own noise could make it harder to hear. For now, the instruments show background activity. Breathing, creaking, exhaling, humming faintly but within normal bounds. The probability of an eruption in any given year is estimated at about 1 in 700,000. These numbers are cold comfort, but they remind us that vigilance is not the same as fear. The planet will warn us. Our responsibility is to remain attentive, to trust the signals over the rumours, and to accept that certainty will never arrive in neat percentages. Volcanoes are storytellers in their own language, and Yellowstone, when it moves again, will not whisper. It will clear its throat first, and loudly. The only uncertainty is how closely we will be listening when that day comes. The mechanics of how we would actually detect these warnings are worth pausing on, because they are often misunderstood. When most people imagine volcano monitoring, they think of a few scientists with binoculars, peering at a mountain slope and scribbling in notebooks. Yellowstone's reality is far more sophisticated. Spread across its plateaus and forests is a quiet army of instruments. GPS receivers fixed into bedrock, seismometers buried in the soil, gas sensors mounted near steaming vents, and even infrasound microphones capable of picking up vibrations below the range of human hearing. None of these devices is dramatic to look at, but together they weave a net of constant surveillance, producing streams of data that feed into servers and modelling software. The park is among the most heavily instrumented volcanic systems in the world, precisely because of the fear its name evokes. One of the most powerful tools now available is satellite radar, known formally as INSAR, Interferometric Synthetic Aperture Radar. Satellites orbiting hundreds of kilometres above Earth bounce radar signals down at Yellowstone and record the reflected waves. By comparing repeated passes, scientists can detect ground movements as subtle as a centimetre, even across the expanse of the entire caldera. This allows them to see deformation patterns invisible to the human eye or even to local instruments. If the ground swells, tilts, or sinks, the satellites pick it up, frame by frame, like a slow-motion film of the Earth's breathing. The irony is that tourists on boardwalks staring at steaming pools often have less idea of what is happening beneath them than a spacecraft flying silently overhead. Alongside satellites, gas monitoring has become increasingly refined. Rather than relying solely on ground sensors, aircraft and drones are flown through plumes above geyser basins, measuring carbon dioxide and sulfur dioxide concentrations. These aerial surveys can cover larger areas more quickly than stationary sensors, painting a moving picture of the volcanic exhalations. If magma were to rise and release a surge of gas, drones would almost certainly register it before humans even noticed an unusual smell. It is a reminder that, for all the mythology around sulfur as a rotten egg warning, our noses are crude tools compared to the instruments now in play. Yet monitoring is only half the equation. The harder challenge is communication. When unusual signals do appear, say a swarm of earthquakes or a pulse of uplift, the scientific response is cautious. Researchers issue statements carefully worded to explain that such behaviour is within the historical range of Yellowstone's activity, even if it draws attention. This careful tone is deliberate because each spike in data is quickly magnified by social media into rumours of imminent catastrophe. Scientists have learned that managing expectations is as important as measuring tremors. After all, Yellowstone has experienced numerous episodes of heightened activity in the past century, none of which led to eruption. Crying wolf too often risks dulling public trust. History offers some sobering case studies in communication. Before the Mount St. Helens eruption in 1980, scientists observed alarming bulges and intense tremors. They issued warnings, but many locals dismissed them as exaggeration, until the mountain exploded. On the other hand, Mount Pinatubo in the Philippines in 1991 showed how effective clear communication can be. Scientists detected the signs early, convinced skeptical leaders to act, and tens of thousands were evacuated before the eruption, saving countless lives. The Yellowstone Volcano Observatory draws lessons from both stories. It is not enough to have the instruments. The public must be ready to believe the signals. Another subtlety is time. Many assume that the sequence of warnings would unfold in a neat, predictable pattern. But volcanoes are messy. Some eruptions give years of advance notice, others only months, and a few surprise even seasoned experts. The longer the lead time, the more complex the human response becomes. Weeks of warning could mean evacuating entire states. Months of warning might spark economic collapse long before magma rises. A century of gradual signals could mean generations living under an indefinite shadow. In each case, the Earth would be speaking. The difficulty lies in how society chooses to live with that message. It is important, too, to remember that not every unusual signal is volcanic at all. Ground uplift can also be caused by shifting groundwater. Earthquake swarms may reflect hydrothermal fluid movement rather than magma. Gas pulses can result from changes in surface permeability. Sorting through these tangled causes requires careful cross-checking of multiple data streams, and even then, uncertainty never vanishes. This is why scientists resist definitive statements. The volcano will tell us much, but it will never hand us a calendar. Perhaps the most haunting element of all this is not whether Yellowstone will erupt. Eventually it will, though likely not in our lifetime, but whether human society can hear subtlety over noise. In a culture accustomed to breaking news alerts and dramatic headlines, the quiet rise of a few centimetres, the deepening hum on a seismogram, the drift of gas ratios, all of these may struggle to compete with rumour. And yet, they are the very signs that matter. If there is a lesson in Yellowstone's monitoring, it is not only that the Earth speaks, but that listening requires patience, trust, and the ability to sit with uncertainty. When thousands of bison head uphill, what are they really telling us? In July of 2025, social media was awash with videos claiming that Yellowstone's wildlife was fleeing the park en masse. Herds of shaggy bison trotted across asphalt, elk moved through meadows, and even grizzlies appeared on the move. The clips were stitched together with ominous captions. They know something we don't. For many viewers, the implication was clear. If the animals were leaving, Yellowstone's supervolcano must be about to erupt. It is an idea so gripping, so cinematic, that it spread far faster than the sober clarifications of scientists who pointed out that bison walk roads every spring simply because they are easier than snow-drifted hillsides. The myth of animals as the Earth's first alarm system has deep roots, but the truth is far more complex. Animals are indeed sensitive creatures. Studies show that some species can detect vibrations far below the threshold of human perception. Elephants in Africa appear to respond to low-frequency rumbles of distant thunder, or even to the seismic waves of far-off storms. Birds have been observed altering flight paths before earthquakes. Fish sometimes beach themselves after subtle undersea disturbances. These observations fuel the hope that creatures might notice what our instruments miss. Yellowstone, with its unique mix of tectonic, volcanic and hydrothermal activity, seems like the perfect place for such a drama to play out. But the evidence here is slippery. Bison, elk and bears follow seasonal cycles that are remarkably consistent. As summer ripens, grasses in the valleys dry out and lose nutrition. The herds climb to higher elevations where cooler temperatures keep vegetation greener for longer. In winter, they descend again, searching for patches with less snow cover and more accessible forage. These migrations are ancient and predictable, carved into instinct by millennia of survival in a landscape shaped by ice and fire. What looks on a viral video like a sudden panic is, more often than not, the normal rhythm of animals following their food. In fact, park rangers note that the timing of these movements matches seasonal expectations so closely that they often use wildlife behaviour as a calendar. When the first groups of bison cross the roads, it is not a sign of doom, but a sign that spring has arrived in earnest. Still, we should not dismiss the question outright. Yellowstone's animals live closer to the ground than we do. Their noses are nearer to soil vents, their lungs breathe the same sulphur-laced air, and their bodies rest on vibrating earth. There have been cases in other volcanic regions where changes in gas emissions caused animals to behave unusually. Carbon dioxide, which can pool invisibly in low-lying areas, has suffocated wildlife near vents in Cameroon and Italy. Dogs, birds, and livestock have all shown sensitivity to elevated gas concentrations before humans recognise danger. Likewise, earthquake foreshocks have been associated anecdotally with restless pets and unusual livestock movements. The possibility that Yellowstone's creatures might react to subtle shifts in gas or tremor is not impossible. It is simply unproven. What complicates matters is scale. Yellowstone averages between 1,500 and 2,500 earthquakes each year, most so small they are never felt by humans. If animals truly fled at every tremor, they would never stop running. Likewise, carbon dioxide and sulfur dioxide seep out constantly, fluctuating with geyser cycles and weather patterns. Any behavioural reaction would need to distinguish between harmless variations and meaningful changes, something even our advanced instruments struggle to do. Expecting a bison to outthink a spectrometer is perhaps asking too much. the myth persists partly because it is comforting. The idea that animals know first suggests that nature itself provides an early warning system, one accessible without satellites or seismometers. It ties us back to an older relationship with the natural world, when reading the skies and the flight of birds was a form of survival. But in Yellowstone's case, the evidence points to a different lesson. The herds move when food dictates, the bears roam when berries ripen, the elk descend when snow deepens. These are vital signals, but they are not predictive of magma on the move. What we do know is that if Yellowstone were preparing for a major eruption, the signs would be unmistakable in the data. Sustained uplift, swarms of earthquakes, sharp gas surges, harmonic tremor. Those indicators would trigger scientific alerts long before animals shifted their migration routes. Wildlife might still react to the changes, but by then humans would already have the evidence in hand. In other words, if the bison ever did stampede for reasons beyond grass and snow, scientists would be running too, not because of instinct, but because the instruments had already confirmed the threat. So what are the animals really telling us? That Yellowstone is alive, dynamic, and still ruled by seasonal cycles older than our species. Their movements are reminders that this landscape is not a zoo, but an ecosystem in constant motion. They may not warn us of super-eruptions, but they do warn us of something equally important: our tendency to misinterpret nature through the lens of fear. A herd jogging along a road is not prophecy. It is survival, and survival is not always dramatic. The haunting question that lingers is whether we can learn to separate signal from noise, whether in the data streams of seismometers or in the hooves of bison crossing a meadow. Because if we cannot, the danger will not be missing the eruption, but drowning in the myths we invent about it. How did 23 bison become 5,000 architects of the plains? To answer that, we have to rewind to the 19th century, when the great herds that once shook the North American continent were nearly erased. Tens of millions of bison roamed from Canada to Mexico, shaping grasslands with their hooves and their hunger. Yet in the span of just a few decades, industrial hunting and government campaigns reduced them to scattered remnants. By the year 1889, fewer than 1,000 were thought to remain in the wild. In Yellowstone, the cradle of the last free-ranging herd, only 23 survived by 1902. It was a biological cliff edge from which a species and an ecosystem almost tumbled. The story since then is a recovery both fragile and astonishing. Through protection inside the national park breeding programs and gradual public revaluation of bison from pest to heritage animal, their numbers have grown to around 5,000 today. These Yellowstone herds are among the very few that still live with minimal human intervention, following ancient migratory instincts across some of the same valleys their ancestors once knew. But the surprise is not just that they survived, it is what they are doing to the land. For much of the 20th century, heavy grazing was seen as a destructive force. When livestock stripped pastures bare, ecologists documented soil compaction, loss of plant diversity, and desertification. The assumption was simple: more mouths meant fewer plants, less resilience, and long-term ecological decline. Yet Yellowstone's bison are showing us something counterintuitive. Recent research published in Science suggests that their grazing is not a liability, but a form of ecological engineering. As herds sweep through river valleys, eating grasses down to stubble, they are effectively supercharging the nitrogen cycle. The plants that regrow after grazing are not weaker but richer, their tissues holding up to 150% more nutrients than ungrazed patches. The mechanism is elegant. Bison clip plants repeatedly, preventing them from becoming tall, woody, and nutrient-poor. Instead, the grasses invest in dense, leafy regrowth that is both more digestible and more nutritious, creating a feedback loop of fertility. Their dung further fertilizes the soil, and their trampling hooves aerate the ground, mixing organic matter back into the earth. The result is not a barren field, but a dense, nutritious pasture that supports a wider web of life. Elk, pronghorn, and even insects and birds benefit from the improved forage. The cycle is reminiscent of the Serengeti, where the recovery of wildebeest herds transformed grasslands by sheer weight of numbers. Yellowstone's bison, though fewer in number, appear to be creating a North American analogue. This has profound implications for conservation. For over a century, managers treated bison primarily as relics, symbols of frontier history, animals to be preserved for their own sake. Now they are being recognized as keystone engineers of entire ecosystems. Their movements across Yellowstone maintain biodiversity in ways that fences and fire suppression never could. Ironically, what humans once called overgrazing is proving to be exactly what these grasslands evolved to expect. Without bison, the system weakens. With them, it flourishes. The journey from 23 survivors to ecological architects also speaks to resilience. Had the Yellowstone herd vanished in 1902, we might never have rediscovered these processes. Grasslands across North America, already fragmented by agriculture and development, would lack their largest natural grazers. The parallels to Europe are striking. Once, aurochs shaped forests and meadows in similar ways, but their extinction 4 centuries ago erased those dynamics. Yellowstone gives us a living laboratory to see what happens when such forces return. And yet, this recovery remains precarious. The 5,000 bison of Yellowstone are hemmed in by park boundaries. When they cross into Montana in winter, searching for easier forage, conflicts with cattle ranchers arise over grazing competition and disease transmission. Each year, some are culled or captured to prevent overpopulation and maintain political balance. The irony is sharp. The same species once nearly exterminated is now managed to prevent it from becoming too many. The ecological lesson, however, is clear. Left to roam at larger scales, bison could restore grasslands far beyond the park's borders, just as wildebeest remade the Serengeti when hunting pressures eased. Perhaps the most humbling part of this story is how long it took us to notice. For decades, ecologists counted bison and measured their range, but it was only with new techniques, soil chemistry analysis, aerial vegetation surveys, long-term grazing plots, that the scale of their impact became visible. The animals were not just surviving, they were cultivating, shaping, engineering. They were not passive relics of prehistory, but active forces of modern ecology. So when we watch a bison herd rolling across a valley floor, it is worth remembering that we are not just seeing big animals in a park. We are seeing architects at work, redesigning the land with each bite and each hoofprint. The haunting question is whether we will allow this role to expand, restoring bison to more of their historic range, or whether we will keep them penned in, their talents confined to a few million acres. Because if 23 survivors can rebuild 5,000 and repair an ecosystem, what might 100,000 do for a continent? The bison's engineering role also extends to the water itself. By grazing intensely in valley bottoms, they alter how snowmelt and rain interact with the soil. Short, dense grasses encourage infiltration rather than runoff, reducing erosion and helping water linger longer in the ground. This slow release supports streams during drier months, effectively buffering parts of the watershed against drought. In a system like Yellowstone, where hydrothermal features, rivers and wetlands are tightly linked, such subtle hydrological influences ripple outward in unexpected ways. Researchers have noted that wetlands used by amphibians, and willow stands important to nesting birds, are healthier in areas shaped by consistent bison activity. Beyond water, their physical presence leaves its own architecture. Wallowing, rolling in the dirt to shed fur and deal with insects, creates shallow depressions that collect rainwater. These wallows become miniature wetlands, habitats for frogs, insects and wildflowers. Over time, a landscape dotted with wallows resembles a mosaic of microhabitats, each a pocket of biodiversity created not by accident but by instinctual behaviour. In this way, the very act of a bison scratching its back or shaking off flies becomes part of a planetary-scale ecological design. Their influence is also cultural, though in ways harder to measure with soil samples. For indigenous peoples across the plains, bison were never just meat on the hoof, but relatives, providers and symbols woven into spiritual life. The near eradication of bison in the 19th century was not only an ecological catastrophe, but a cultural wound. The return of herds to Yellowstone and beyond carries meaning that transcends numbers on a census sheet. Each animal is both a grazer and a reminder that landscapes and identities can be remade, even after devastation. When modern science now celebrates the nitrogen feedback loops and biodiversity benefits of bison, it echoes knowledge long held by those who lived with them for millennia, the understanding that people, animals and land shape one another continuously. The The global implications of this story are quietly radical. For decades, conservation biology has often emphasized protection of species in isolation, saving a bird, a mammal, a tree. But the lesson of Yellowstone's bison is that protecting a process can matter more than protecting a species. Their grazing is not just a habit. It is an ecological function, one that turns sterile grasslands into nutrient-rich pastures. The same principle might apply elsewhere. Elephants opening forests in Africa, caribou trampling snow to reveal forage in the Arctic, kangaroos reshaping Australian grasslands. Bison remind us that the survival of ecosystems depends less on preserving snapshots of wilderness and more on keeping the great engines of animal movement running. In that sense, Yellowstone's bison are not just survivors of a 19th century slaughter. They are guides to a future where conservation may focus less on museums of fenced animals and more on restoring migration, energy flow, and resilience. It is an idea both hopeful and daunting, because it suggests that the path forward requires more space, more tolerance, and more humility than we usually allow. The question lingers, will we see the bison simply as relics of what was lost, or as teachers of what can still be rebuilt? What happens when boiling water suddenly blows the ground apart? For most visitors to Yellowstone, the danger seems obvious in the form of steaming pools and splashing geysers, yet the real hazard lies in something less visible and more unpredictable: hydrothermal explosions. Unlike a volcanic eruption that sends magma to the surface, a hydrothermal explosion is powered by water. Superheated groundwater trapped beneath a fragile layer of rock or clay can flash into steam if the pressure changes. When it does, the expansion is violent enough to hurl mud, rocks, and boiling water outward, tearing a new crater in the ground. These events are not rare in Yellowstone. They are part of its living pulse, small-scale reminders that the Earth does not need magma to reassert itself. The most recent case came to light between late December of 2024 and early February of 2025 in the Porcelain Basin of Norris Geyser Basin, one of the park's most dynamic areas. Rangers and scientists were performing routine checks of logging equipment when they noticed something new: a circular pool of light blue water about 4 meters across. It sat quietly west of an area informally called Tree Island. Around it lay scattered rocks, some as wide as 30 centimeters, coated with pale grey mud. The texture of the deposit and the arrangement of the rocks told a clear story. At some point in the previous weeks, a hydrothermal explosion had torn open the crust, blasting debris outward and leaving behind a newborn pool that now steams under the Yellowstone sky. Pinpointing when this explosion occurred required tools beyond human eyes. High-resolution satellite images showed no sign of the pool in mid-December of 2024. By early January of 2025, a shallow depression appeared, and by February the feature was fully developed and filled with water. These images provided a narrow window of formation that no ranger on the ground could have caught. Adding to the picture was infrasound data, collected by a station installed in September of 2023. On December 25th, the instruments recorded a subtle acoustic signature consistent with a hydrothermal explosion. Curiously, it was not accompanied by a seismic signal, confirming that while the event was forceful enough to shake the air, it did not resemble an earthquake. The new pool was small, harmless in appearance, and far from boardwalks or trails. Visitors walking nearby in spring or summer would likely miss it altogether, but to scientists, its significance was large. It demonstrated the power of Yellowstone's monitoring network, which now includes satellites, drones, infrasound sensors, and seismic arrays. Without these systems, the event would have been invisible, filed away as just another anonymous change in the steaming patchwork of Norris. Instead, researchers can now trace its timing, its mechanics, and its role in the broader cycle of Yellowstone's hydrothermal evolution. The fact that they can capture such minor explosions speaks to how far monitoring has come in just a few decades. Hydrothermal explosions at Yellowstone are not only modern curiosities. The landscape is scarred with craters from much larger blasts, some hundreds of meters wide, formed in the past 15,000 years. These are reminders that while magma-fed eruptions at Yellowstone are rare on human timescales, water-driven explosions are relatively common. They do not produce lava flows or continent-wide ash, but they can devastate areas the size of football fields or more. They are also the hazard most likely to affect tourists. Several documented fatalities in the park have come not from bears or bison, but from accidents near boiling pools where thin crust collapsed or scalding water surged unexpectedly. For all the fascination with supervolcanoes, it is these hydrothermal features that remain Yellowstone's most immediate threat. Porcelain Basin in particular has a reputation for volatility. Its ground is thin, its vents numerous, and its chemistry constantly shifting. Geologists often describe it as one of the most dynamic hydrothermal fields on Earth. That dynamism is why the new pool there drew attention. It was not unusual in its size, but it symbolized the constant churn beneath the surface. Hot water circulates through fractures, dissolving minerals, depositing new ones, and occasionally plugging conduits until pressure builds. When the seal breaks, the result can be an explosion that sculpts the surface in moments. Seen in this light, Yellowstone is not a static wonderland of geysers, but an active experiment in geologic engineering, running continuously beneath our feet. The unsettling truth is that no one can predict precisely when or where the next hydrothermal explosion will occur. The signs are subtle, the triggers varied, and the scale uncertain. Some are minor, like the Porcelain Basin pool, producing a small crater and little else. Others in Yellowstone's past have been fierce enough to fell forests and leave depressions that remain visible millennia later. If the supervolcano is the park's slow heart, then hydrothermal explosions are its skipped beats, sudden, jarring, and dangerous precisely because they are local and unpredictable. So what happens when boiling water blows the ground apart? On one level, you get a new pool 4 meters across steaming quietly beside Tree Island. On another, you get a reminder that Yellowstone is not frozen in postcard beauty. It is restless, alive, and far more dangerous in its day-to-day breath than in its rare geological outbursts. The haunting question, as we walk the boardwalks and watch tourists lean too far over railings, is whether we grasp this. Do we see the ground beneath us as solid, or do we accept that it is temporary, waiting for the moment when heat and pressure decide to reshape it once again? If the Porcelain Basin pool was a reminder of Yellowstone's volatility on a small scale, it also serves as a window into the invisible processes shaping the park every day. Hydrothermal explosions do not require a dramatic build-up to be significant. Even modest blasts rearrange mineral deposits, rechannel water, and alter the chemistry of nearby features. Over time, dozens or hundreds of these quiet events slowly sculpt the geyser basins into the shifting patchwork we see today. To call Yellowstone a landscape is misleading. It is more accurate to think of it as a laboratory under constant renovation, with nature itself as the builder. Part of what makes these explosions so unnerving is their element of surprise. Unlike larger volcanic eruptions that give warning through earthquakes, swelling, and gas emissions, hydrothermal blasts can occur with almost no precursors detectable by humans. A vent becomes clogged, pressure rises, and within moments the ground ruptures. For park managers, this is a nightmare scenario. It means that even in areas considered safe, change can come suddenly. Boardwalks and viewing platforms are placed carefully to avoid known hazards, but history has shown that the ground's memory is longer than ours. Craters filled with pools today may conceal scars of much larger blasts from centuries past, forgotten until they return. The December 2024 event also demonstrated the importance of modern tools in catching what older generations would have missed. The infrasound sensors, for instance, are a relatively new addition to Yellowstone's monitoring suite. Unlike seismic instruments that detect ground shaking, infrasound records low-frequency acoustic waves travelling through the atmosphere. These waves can come from avalanches, meteors, or, in this case, hydrothermal explosions. What makes them powerful is that they can capture events too small to register as earthquakes, yet too forceful to be ignored. The December 25th signal, faint but clear, gave scientists confidence that the pool's origin was explosive rather than gradual subsidence. It is one more example of how 21st century monitoring can transform a fleeting natural event into a permanent scientific record. For visitors, the implications are simple but sobering. The serene beauty of Yellowstone's pools and geysers masks the danger that lies just beneath the crust. A crust that, in many places, is only a few centimeters thick, fragile enough to collapse under the weight of a human foot. Warnings to stay on boardwalks are not overcautious bureaucracy. They are lessons written by past accidents. To fall through that thin shell is to meet the same boiling waters that power hydrothermal explosions. For the Earth, that is chemistry. For us, it is lethal. The haunting takeaway is that Yellowstone does not need its magma chamber to remind us of risk. Its water alone, trapped and superheated, is enough to reshape landscapes and rewrite lives in seconds. And while satellites, drones and sensors are improving our ability to watch, there will always be gaps, always be moments where the Earth asserts itself before we can respond. The question that remains is whether we accept this unpredictability as part of the bargain in visiting such a place, or whether we forget, lulled by beauty, until the ground decides otherwise. If there is one thing more dangerous in Yellowstone than bears, bison, or even the supervolcano itself, it is the water. Pools that shimmer in deep blues, greens and reds are not simply hot. They are boiling, acidic, and often deadly. To a human, they are places where a single misstep can be fatal, and yet, to some of the most ancient organisms on Earth, they are home. These beings, called Thermophiles, thrive where we would dissolve. The strange paradox is that Yellowstone's deadliest features are also living archives of life's oldest survival strategies. The word thermophile literally means heat lover. They are bacteria, archaea, and fungi that have evolved to prefer environments hotter than boiling water. Temperatures of 100 degrees Celsius are not a threat, but a baseline. Some species can even persist at 120 degrees, where water remains liquid only because of extreme pressure. This resilience comes from the architecture of their proteins and membranes. Where ours fall apart, theirs remain stable. To stand on the boardwalks of Yellowstone and watch steam roll across a coloured pool is to look at the same survival toolkit that shaped the dawn of life. The story begins not in Wyoming, but billions of years ago, when Earth itself was a hostile place. Oceans were hot, volcanic gases filled the air, and sunlight reached the surface filtered through a haze of methane. In those early days, before plants, before animals, before oxygen itself, microbes that could withstand extremes ruled the planet. Many researchers believe that Thermophiles, or their ancestors, were among the very first organisms to evolve. They were not side characters, but the main experiment of life itself. Without their capacity to harness energy in scalding environments, there may never have been a foundation for more complex life. Yellowstone today is therefore less a park and more a time capsule. Its hot springs recreate the conditions under which life was forged. One of the most famous of these organisms was discovered in 1966, Thermus aquaticus. At first it seemed like just another odd bacterium in a park full of curiosities, but what mattered was not what it looked like under a microscope, but what it could do at a molecular level. Its enzymes, called Taq polymerase, did not unravel at high temperatures. This single fact unlocked a revolution. Scientists realized they could use these enzymes to copy DNA at high heat without them breaking down. The technique became known as the polymerase chain reaction, or PCR. In the late 20th century, PCR transformed biology. It allowed us to amplify tiny fragments of DNA into quantities large enough to study, map, and manipulate. It is the reason genome projects exist, the reason forensic science can identify a criminal from a hair follicle, and the reason doctors could detect a virus in your body within hours. For most people, PCR only became a household term during the global pandemic, when nasal swabs and lab tests determined whether someone carried a virus. But its roots lie in Yellowstone's boiling pools. A microbe clinging to life in scalding water became the silent partner in modern medicine. Few national parks can claim that their residents helped win a Nobel Prize in chemistry. Yellowstone can. Yet the importance of thermophiles goes beyond diagnostics. Today, cyanobacteria living in these pools are at the centre of research into sustainability. They are masters of photosynthesis, capable of converting carbon dioxide and nitrogen into usable forms of energy even under extreme conditions. Where crops wither, they endure. That endurance is now being harnessed to design biofuels and bioplastics. Imagine a fuel source grown not in fertile fields but in vats of heated water, seeded with microbes. These are not science fiction prototypes but active research projects, many inspired by lessons learned from Yellowstone's microscopic residents. The vibrant colours in pools like Grand Prismatic are not mineral paints, but the living pigments of microbial mats. Orange, yellow, and green rings represent different species of thermophiles, each tuned to thrive at a specific temperature band. Together they form a gradient that is both beautiful and informative. By studying these rings, scientists can measure temperature shifts and chemical balances. In a way, the microbes are self-organizing thermometers, reporting conditions with their own bodies. What is striking is that the very organisms that first altered Earth's atmosphere billions of years ago still leave visible traces of their activity today. The larger implication is humbling. For all our technology, we are still borrowing strategies from microbes. Their resilience to heat, acidity, and pressure shows us what is possible in chemistry, agriculture, and energy. They are older than our species, older than our genus, and possibly older than the oxygen we breathe. Yellowstone reminds us that survival on this planet has never been about strength or intelligence alone. It has often been about finding ways to endure in places that seem unlivable. The haunting question is what else lies in those pools, waiting to be noticed. Thermus aquaticus was once invisible until a single discovery rewrote science. Today, with new sequencing technologies and bioengineering tools, researchers suspect we have barely scratched the surface of Yellowstone's microbial library. Each pool may hold another enzyme, another adaptation, another revolution. The danger is that while we marvel at the park's surface beauty, we may overlook its true legacy, the creatures that wrote the first chapters of life and may yet help us write new ones. And so, when you look at a steaming pool, you're not only looking at boiling water, you're looking at echoes of the earliest Earth and hints of the future. Yellowstone's thermophiles are reminders that survival is not about comfort but adaptation, and that life's most important secrets may be hidden where we least expect them, in places too hot for anything else to endure. There is also something quietly philosophical about these organisms. We tend to imagine ourselves as the pinnacle of evolution, yet it is the microbes of Yellowstone that have proven most durable across geological time. Dinosaurs flourished and vanished. Mammoths came and went. Empires rose, collapsed, and left ruins. But the descendants of ancient thermophiles are still here, bubbling away in steaming runoff channels, indifferent to human timelines. From their perspective, we are the fragile experiment. Our civilizations have lasted for only a flicker of their existence, while they have endured the slow rearrangements of continents, the waxing and waning of ice ages, and even the impact of asteroids. This perspective changes how scientists think about resilience. Thermophiles are not simply curiosities to be catalogued, they are living case studies in how life solves problems. Their enzymes are models of efficiency under stress. Their cell membranes demonstrate molecular strategies for surviving chemical assault. Even their pigments, which absorb and reflect a light in strange wavelengths, have inspired materials research. In every adaptation, they reveal a principle that might be borrowed for human use. The paradox is that the most primitive forms of life are also the most technologically promising. Their presence also forces us to reconsider where life might exist beyond Earth. When probes scan the icy moons of Jupiter or Saturn, or when rovers crawl across Mars, they are searching for traces of microbial communities that could look very much like Yellowstone's. Pools on Europa or Enceladus, kept warm by geothermal activity beneath thick ice, may mirror the niches Yellowstone microbes occupy today. If life can persist in boiling acid pools on Earth, why not in a saltwater vent beneath an alien crust? In this sense, every hot spring in the park doubles as a training ground for astrobiology. By studying thermophiles, we prepare ourselves to recognize their cousins elsewhere in the solar system. And then there is the question of what Yellowstone's microbes might yet contribute to medicine. Already, enzymes from thermophiles are being adapted for industrial processes ranging from laundry detergents to genetic engineering. But research is moving further, toward pharmaceuticals that remain stable at high temperatures, and toward bioreactors designed to produce useful compounds without the need for costly refrigeration. In an age of climate change, when stability itself is becoming scarce, these organisms may hold the key to building infrastructure and technologies that can withstand volatility. Standing at the edge of a steaming pool, then, is not only a tourist's experience, it is a glimpse into life's oldest tricks, its most resilient adaptations, and perhaps its future tools. The beauty of the scene, the rainbow bands of microbial mats, the curling steam, the sulfur-scented air, conceals a deeper truth. Yellowstone is not only a volcanic wonder, but also a biological archive, and the creatures thriving in its boiling waters remind us that sometimes the smallest life forms leave the largest legacy. Yellowstone is often imagined as a place of stillness, bison grazing across valleys, steam drifting from pools, and a lake lying flat beneath distant mountains. But if you were to listen beneath the quiet, the ground tells another story. It never sleeps. Yellowstone shivers and ticks like a restless clock, producing around 1,000 to 3,000 earthquakes every single year. Most are so small they are never felt by a visitor, but their sheer number raises a haunting question. Why does this place shake so constantly, and what does it mean when the tremors come not as isolated jolts, but as swarms? To most people, the word earthquake suggests one big rupture followed by a cascade of aftershocks. A city crumbles, and smaller quakes rattle nerves for days after. Yellowstone, however, often flips that pattern. Here, earthquakes arrive in clusters called swarms. Instead of one dominant event and a fading tail of aftershocks, swarms are built of hundreds of similar-sized quakes that come and go without a single main shock. To a seismologist's graph, the difference is clear. To a camper who feels the ground ripple beneath a tent, the experience may be equally unsettling. The swarms are not random. They tend to cluster around areas where faults cut through the crust, or where hot fluids move beneath the surface. Yellowstone sits atop a fragile lattice of fractured rock, saturated with superheated water and under pressure from deeper magma. When water shifts suddenly into a crack, it can trigger slip along small faults, setting off a chain reaction. One jolt destabilizes the next, and a storm of minor quakes begins. To the instruments that monitor them, these swarms can look like chatter in the Earth's language, bursts of static marking movements too subtle for human senses. One of the most notable examples came in 1985, when a swarm rattled the northwest edge of the park near Hebgen Lake. For several months, hundreds of quakes kept the region unsettled. None were large enough to cause damage, but the sheer persistence made geologists sit up. Was this the beginning of something larger? In the end, the swarm faded, leaving behind not devastation but a better appreciation of how alive Yellowstone's crust truly is. In the winter of 2008, another swarm struck, this time beneath Yellowstone Lake itself. Over several weeks, more than 800 small quakes rippled under the frozen surface. Most were too small to be felt, but the pattern was unmistakable. The activity raised concern not because of immediate danger, but because it reminded scientists how easily stress moves through the system. A shift under the lake hinted at fluids finding new pathways, possibly reorganizing the plumbing beneath one of the park's most iconic landscapes. Again, the swarm eventually quieted, yet it underscored the fact that Yellowstone's calm appearance is a mask stretched over a shifting, pressurized reality. The most recent swarm to draw public attention came between 2021 and 2022, with hundreds of events recorded near the Norris Geyser Basin. To some observers, the sheer number felt ominous. Social media, never shy of speculation, filled with warnings of imminent eruption, but geologists countered with context. Yellowstone swarms are not unusual. They are part of the park's daily breathing. In fact, most swarms never result in any visible change at the surface. They are less a harbinger of doom than a reminder of how complex and dynamic the underground system is. If anything, the absence of swarms would be stranger. Part of the challenge lies in how swarms blur the boundary between tectonic and volcanic activity. Some are triggered by ordinary fault slips, the same processes that drive quakes across mountain ranges worldwide. Others are clearly tied to the movements of hot water and steam through porous rock. And occasionally, magma itself may be the driver, forcing open space as it shifts position deep below. For scientists, separating these causes requires careful analysis of depths, patterns, and frequencies. What may look like a frightening burst of activity to the untrained eye often reveals itself as nothing more than the crust adjusting to its own fragility. Yet the swarms matter. They are not ignored or dismissed. Each one feeds into the broader understanding of Yellowstone's structure, adding another layer of data to the maps of stress and fluid pathways. By tracking them, Seismologists can refine models of where magma sits, where water circulates, and how pressure is released. Each swarm is both a puzzle and a rehearsal, a way of asking how the system might behave if larger forces were ever at play. For the casual observer, the question lingers. If Yellowstone shakes thousands of times a year, how would anyone know if one swarm marked the beginning of something more dangerous? The unsettling truth is that no single tremor or cluster holds the answer. Only patterns across months and years reveal whether stress is building toward eruption or simply relieving itself in small doses. Scientists admit the limits of prediction, but they also emphasize that the very presence of monitoring networks, hundreds of seismometers feeding real-time data, means that if Yellowstone were to shift toward a dangerous state, the signs would not be silent. The haunting resolution is this: Yellowstone will always shake, swarm, and rattle. Its restlessness is not a warning of catastrophe, but a condition of existence. To walk its trails is to step across a crust that is never entirely still. The question is not whether the ground will move, but how often, how subtly, and with what consequence. And if swarms are the background noise of this great caldera, then listening to them may be the best way we have of staying connected to the living, breathing earth beneath our feet. Every time Yellowstone enters the news cycle, someone inevitably asks the same question. If the supervolcano is so dangerous, why don't we just stop it? Couldn't we drill a hole, bleed off the pressure, and save the world? It sounds like a reasonable idea, at least until you pause to consider the scale of what is actually sitting beneath Wyoming. To imagine controlling Yellowstone by drilling is a bit like trying to let the air out of a hurricane with a pin. The proposals come in many flavours. Some suggest drilling into the shallow magma chamber to release pressure. Others imagine pumping in water to cool the system, as if treating a kitchen stove left too long on high. A few envision vast geothermal plants siphoning off heat for electricity while lowering the risk of eruption. On paper, it is simple. In practice, it is absurd. The upper magma chamber alone is estimated to contain thousands of cubic kilometres of partially molten rock. To meaningfully alter its temperature or pressure would require a drilling operation larger than anything humanity has ever attempted, running not for years but for geologic epochs. There is also the small matter of unintended consequences. Magma is not a passive reservoir waiting politely behind a valve. It is a complex mixture of melt, crystals, and gas under immense pressure. Drill into it the wrong way, and instead of releasing pressure slowly, you might create a trigger. The result would not be a controlled vent, but a catastrophic eruption brought on prematurely by human error. Scientists who study volcanoes tend to frown on the idea of poking at them with giant straws. Even geothermal energy, which is often proposed as a win-win solution, comes with complications at Yellowstone's scale. Around the world, geothermal plants tap hot water systems to produce power. They are effective where reservoirs are well understood and relatively small. Yellowstone is neither. Its hydrothermal systems are vast, interconnected, and precariously balanced. Attempting to divert them could destabilize the very features visitors come to see: geysers, hot springs, and fumaroles. The same water that could spin turbines is also the water that makes Old Faithful erupt on schedule. And unlike a private energy company, the National Park Service does not consider destroying one of Earth's greatest natural wonders an acceptable trade-off for a few gigawatts of electricity. There is also the matter of cost. A NASA-linked study once speculated that cooling Yellowstone's magma chamber by artificial means might, in theory, reduce eruption risk. But the logistics read like science fiction. You would need to inject massive amounts of water into the crust for tens of thousands of years, at a price tag in the trillions of dollars. Even if you succeeded, the side effects, seismic activity, ground deformation, and unpredictable hydrothermal explosions, could render the area uninhabitable anyway. It would be like spending a fortune to prevent a house fire by flooding the entire neighbourhood. When weighed against the realities of geology, drilling schemes look less like safety measures and more like hubris. Yellowstone is not a pressure cooker waiting to blow its lid. It is a dynamic volcanic system that waxes and wanes on timescales beyond our control. Pressure is released constantly through earthquakes, geysers, gas emissions, and uplift cycles. The idea that humans could step in and manage this system as though it were a leaky faucet betrays both a misunderstanding of scale and an overconfidence in technology. The lightly humorous part is that the Earth does not need our help to erupt. It has been doing it long before humans appeared and will continue long after we're gone. Drilling Yellowstone to prevent an eruption is a little like telling the sun to stop rising. The best we can do is watch, measure, and prepare for what nature decides. For now, monitoring networks are far more effective than imaginary cooling projects. Instruments can warn us of changes, giving time to respond. Drills, on the other hand, would only add another layer of danger. The haunting resolution is this: our tools are mighty in human terms, but Yellowstone does not operate in human terms. To imagine controlling it is to imagine taming plate tectonics itself. The question is not how we might stop it, but whether we can learn to live with the knowledge that some forces lie permanently outside our grasp. And perhaps the humbler, wiser response is not to drill into the supervolcano, but to drill into our own expectations, accepting that the planet is not ours to engineer on every scale, and that awe sometimes comes with limits. The impulse to control Yellowstone by mechanical means also reveals something deeply human. When confronted with overwhelming natural forces, our first instinct is to reach for tools. We dam rivers, divert floods, and build seawalls against the ocean. In many places, such efforts have worked well enough to convince us that every threat can be engineered into submission. But Yellowstone is a reminder that not all hazards operate on a scale compatible with human intervention. A river is a narrow ribbon of water. A volcano is the beating heart of the planet's crust. History offers small but telling examples of where interference with volcanic systems has been attempted. In Iceland in 1973, during the eruption of Eldfell on the island of Heimaey, engineers pumped seawater onto advancing lava flows to slow and divert them away from the town's harbour. Remarkably, it worked, and the harbour was preserved. On paper, this looks like proof that humans can manage volcanoes. Yet the difference is scale. Eldfell's eruption produced a volume of lava small enough to be influenced by water hoses and pumps. Yellowstone's eruptions produce volumes of magma thousands of times larger, stored miles below ground. No fire hose, no matter how ambitious, could reach that deep. Even where interventions succeed, they often come at a cost. Cloud seeding has been used to coax rain from stubborn skies, but with uncertain long-term consequences. Megadams have tamed rivers only to disrupt ecosystems and displace millions of people. These examples remind us that fixing nature can create as many problems as it solves. A project aimed at cooling or drilling Yellowstone would be magnified by orders of magnitude, and the unintended side effects would likely be catastrophic. There is also the question of politics. Yellowstone is not an isolated volcano in a remote corner of the world. It sits within a heavily visited national park, drawing millions of people every year, and within a federal system that places high value on preservation. Even if drilling or cooling were technically feasible, the legal and ethical battles would be immense. Who would grant permission to puncture a protected landscape in the name of an uncertain experiment? And who would accept responsibility if it went wrong? The more one imagines the logistics, the more the idea collapses under its own weight. Some proposals repackage the idea under the banner of renewable energy. What if Yellowstone could power the entire United States with geothermal energy? Technically, the heat flux is immense, enough to supply vast amounts of electricity, but technically does not mean practically. To build geothermal plants at that scale would mean industrializing one of the most celebrated natural landscapes on Earth. The geysers, hot springs, and microbial mats that attract scientists and visitors would be altered or destroyed. And ironically, draining the hydrothermal system too aggressively might destabilize the very features that make Yellowstone unique, converting beauty and science into an industrial park. Even if all these barriers were somehow overcome, the payoff would remain uncertain. Cooling a volcanic system is not like turning down the thermostat in a house. The Earth is constantly resupplying heat from below, fed by a mantle plume that rises from hundreds of kilometers deep. Any cooling project would be a temporary measure at best, constantly fighting a supply line of heat that dwarfs human technology. In other words, Yellowstone is not a problem that can be solved. It is a process that must be lived with. The futility of drilling proposals is not meant to inspire despair, but perspective. For most of our species' history, survival meant adapting to the world, not attempting to redesign it. Only in the last few centuries have we begun to imagine ourselves as engineers of planetary systems. Yellowstone reminds us that humility remains a necessary survival strategy. Instead of asking how we can stop it, the more constructive question is how we can prepare, through monitoring, communication and resilience, to live on a planet where some forces remain permanently beyond our control. The haunting irony is that our efforts to control Yellowstone might say more about us than about the volcano. The caldera does not need our drills or our cooling schemes. It will do what it has always done: breathe, shake, uplift, and occasionally erupt. The question is whether we are willing to accept that truth. In the end, the fantasy of drilling Yellowstone is not a plan to save humanity, but a story we tell ourselves to feel less helpless. And perhaps the healthier response is to sit with that helplessness, to learn from it, and to let Yellowstone remind us that we are participants in the Earth's story, not its authors. It is one thing to talk about Yellowstone as a geologic puzzle, a restless caldera that lifts and sighs beneath forests and lakes. It is another thing entirely to imagine the unthinkable: what would actually happen if the supervolcano erupted again. To make sense of this, scientists have constructed models, not predictions but scenarios, to explore what the first 72 hours might look like. It is a sobering exercise, not because anyone expects it soon, but because imagining the opening days helps us understand both the power of the Earth and the limits of human preparation. The first moments would not be subtle. If Yellowstone were to shift into full eruption, the initial sign would likely be a violent explosion near the centre of the caldera. A column of ash and gas would surge upward, carried by the force of expanding gases in magma suddenly released to the surface. Within minutes, that column could rise tens of kilometres into the sky, punching into the stratosphere and casting a shadow across the valleys below. To anyone nearby, there would be no mistaking what had begun. Around the caldera itself, the most immediate danger would be pyroclastic density currents, avalanches of hot gas, ash and rock moving faster than any human or vehicle could escape. They would surge outward from vents at highway speeds, obliterating forests, lake shores and towns within tens of kilometres. No evacuation plan could outpace such flows. The zone of instant devastation would include much of northwestern Wyoming and parts of neighbouring Montana and Idaho. It would be in effect the erasure of everything in the caldera's footprint. For those outside the range of pyroclastic flows, the next danger would come from the sky. Within hours, the ash column would spread laterally as upper winds carried particles eastward. Fine ash, made of pulverized volcanic glass and minerals, is light enough to drift for hundreds of kilometres. Coarser fragments would fall quickly, blanketing the region surrounding the park in layers thick enough to collapse roofs and bury vehicles. The nearest towns, Cody, Jackson, Bozeman, would be coated in choking darkness. Roads would vanish under ash drifts. Power lines would fail under the weight, and emergency response would be reduced to survival. Within the first day, air travel across the western United States would grind to a halt. Jet engines cannot function in ash clouds, which melt into glassy coatings inside turbines. Commercial aviation relies on avoiding volcanic plumes, but a Yellowstone eruption would fill so much of the sky that rerouting would become impossible. Flights would be cancelled en masse, leaving airports filled with stranded passengers. For the first time in aviation history, an entire continent's skies might fall silent. Power systems would follow. Ash is conductive when wet, and even dry deposits can short-circuit electrical grids. Substations and transformers would clog and arc, leading to cascading failures across the Rocky Mountain region. Natural gas infrastructure, with its reliance on compressors and turbines, would suffer similar disruptions. The first 72 hours would not only erase the physical landscape near Yellowstone, but also disable much of the technological landscape far beyond it. Communication networks would struggle as well. Satellite signals can be scattered by dense ash plumes, and ground-based infrastructure would choke with static discharges. Emergency managers would attempt to issue warnings, but the collapse of cell towers and internet cables under ash loads would leave many isolated. In the vacuum of information, rumours would spread faster than facts, as they always do. By the second day, ash would have spread across the Great Plains, carried by prevailing winds. Cities like Denver, Omaha and Kansas City might find themselves under several centimetres of ash. For rural communities, That would mean contaminated water supplies as particles clogged reservoirs and rivers. For urban centres, it would mean a halt to transportation and commerce as trucks and trains failed to move across abrasive surfaces that grind down engines and clog air filters. Livestock exposed to ashfall would face respiratory distress. Farmers would be forced to shelter animals indoors, but even then the infiltration of ash into feed and water would create shortages. By the end of the second day, it would become clear that this was not only a geological event but an agricultural and economic one as well. The third day would bring a strange and unsettling quiet. By then, the heaviest ashfall would have spread eastward toward the Mississippi River Valley, blanketing cities and farmland alike. Across the west, communities would remain shrouded in grey, with sunlight dimmed and air filled with the acrid sting of volcanic glass. Rescue operations in the immediate blast zone would be impossible. Survival efforts would focus instead on those hundreds of kilometres away who face suffocation, thirst, and cold. Scientists emphasise that these scenarios are not predictions but models, based on comparisons with past eruptions and present-day data. They remind us that Yellowstone eruptions are rare, and that the odds of one occurring in any given year are vanishingly small. Yet they also admit that if such an event did begin, the first 72 hours would be unlike anything humanity has ever faced. The haunting question that lingers is not only what the Earth could do in such a short span, but how humans would respond when confronted with forces so far beyond their control. Would the first 3 days be remembered as the opening of an age of resilience, or as the beginning of a story in which our technologies proved fragile against the breath of the Earth? If the first 3 days of a Yellowstone super-eruption would be chaos, the weeks and months that follow would be something different, slower, heavier, and in many ways more dangerous. What remains after the eruption column collapses and pyroclastic surges burn their way across Wyoming is not silence, but ash. And unlike the drama of fire and thunder, ash lingers. It spreads, it seeps into every surface, and it reshapes life in ways both obvious and hidden. To imagine the ash world is to imagine an entire continent buried under the finest glass shards nature can make. Volcanic ash is not ash in the ordinary sense. It is not soft wood soot or the remains of something that once burned. It is shattered rock, a dust born of violent expansion. Magma is ripped into particles as gas explodes out of it, grinding molten stone into pieces so small they can float for hundreds of kilometres. Under a microscope, each particle is a jagged shard, sharp enough to slice tissue, small enough to be inhaled deeply into the lungs. To the naked eye, it looks like grey powder. To an engineer or doctor, it looks like a universal hazard. In the weeks after Yellowstone's eruption, prevailing winds would determine the pattern of its reach. Atmospheric modelling suggests that half the United States could be covered in varying depths of ash. Wyoming, Montana, and Idaho would be smothered in meters. Further east, Nebraska, the Dakotas, Kansas, the ash might be measured in tens of centimeters. Even the Midwest could find itself under a thin but unrelenting dusting. And ash does not fall like snow. It compacts, it hardens when wet, it clogs drains and gutters until rain turns it into cement. The first true crisis after the eruption would be structural. Roofs collapse under load. Engineers estimate that even 10 centimeters of wet volcanic ash can overload typical residential structures, especially when rain follows fall. Barns, warehouses, schools, none are designed for the weight of cement powder accumulating day after day. In a Yellowstone ash world, whole neighbourhoods might vanish beneath their own ceilings, not in fire but in failure. Insurance would be irrelevant. Repair would be impossible when half the country's transport network is impassable. Transport would be the second crisis. Ash is abrasive. It chews through moving parts with relentless speed. Car engines choke, air filters clog, train wheels grind down, airplane turbines melt into useless glass. Even military hardware designed for deserts has failed in past ash clouds. In the weeks following eruption, much of the American interior would effectively become cut off, not because the land was destroyed, but because every machine that makes movement possible would fail. Resupply would slow to a crawl. Water would become the third crisis. Ash is a perfect contaminant. It coats reservoirs, clogs rivers, and leaches acids into supply systems. Municipal treatment plants already strained by power loss, would be overwhelmed by the volume of suspended particles. Rural wells would clog with slurry, livestock would drink poisoned streams. For cities, the problem would not only be scarcity but toxicity. Inhaled, ash scars lungs. Ingested, it irritates and inflames. Mixed with water, it becomes mud that moves like cement. In a matter of weeks, water would no longer be guaranteed safe in much of the central and western United States. The fourth crisis would be health. Volcanologists who have studied ash under microscopes emphasize that it is a respirable hazard. Each particle acts like a splinter, embedding in lung tissue. Short exposures can cause coughing fits and inflammation. Long exposures can lead to silicosis, a progressive and irreversible disease in which lungs slowly stiffen as scar tissue builds. Fossil beds in Nebraska remind us that even animals 1,000 miles from an eruption can succumb to these effects. In humans, with longer lifespans and chronic exposures, the toll would be measured in years. Masks could help, but distribution on the scale required would be a logistical impossibility once transport systems fail. Even electricity would not return quickly. Ash short-circuits transformers, coating insulators with conductive films when wet. In Iceland, engineers learned this lesson during the Eyjafjallajökull eruption in 2010. In a Yellowstone event, with orders of magnitude more ash, regional grids might be disabled for months. Hospitals running on generators would eventually run out of fuel. Refrigeration for food and medicine would fail. The ash world is not only grey in colour but in consequence. Agriculture would collapse as fields vanish under abrasive layers. Even shallow ashfall makes land temporarily infertile, not because the soil itself is ruined, but because seeds cannot germinate beneath the smothering cover. Tractors cannot run, irrigation cannot pump, and livestock cannot graze. Within weeks, the United States, normally a breadbasket, would become a nation without harvest. The ripple effects would travel outward as trade halts and global markets convulse. Yet perhaps the most insidious quality of the ash world is psychological. In the immediate disaster, adrenaline carries people through. In the weeks after, when the sky remains dim and the ground remains clogged, despair sets in. Past volcanic crises show that survivors are often not defeated by fire but by the slow grind of dust. What does it mean to live in a landscape where every breath is dangerous, every step crunches with glass, and every horizon fades into grey? Scientists do not raise these questions to frighten but to prepare. The ash world is not certain, nor is it imminent. It is simply one possible outcome of a system that has behaved this way before. In trying to map its consequences, we remind ourselves that the Earth operates on scales of force and time that dwarf human expectation. The haunting question is not whether ash could cover half a continent, but whether we have the patience to imagine life after the third week, when headlines fade but the dust remains. Adaptation in an ash world would not be impossible, but it would be improvisational. Farmers, for instance, would quickly discover that their normal tools had become useless. Tractors clog, irrigation systems fail, and livestock collapse from lung damage. The solution, if it could be called that, would lie in old methods. Farmers might scrape ash by hand from portions of fields to expose soil, planting hardy crops directly into cleared rows. Goats and sheep capable of surviving on tougher forage might outlast cattle, though even they would cough on the abrasive air. In many regions, barns would no longer be storage for feed, but makeshift shelters where livestock could be kept away from ashfall. City dwellers would face a different set of improvisations. Without reliable water, the act of boiling or filtering ash-laden supplies would become central. Volcanic ash does not dissolve, so it could be filtered with cloth or allowed to settle, but neither process removes the chemical components entirely. Small communities might rediscover techniques once common on the American frontier, collecting rainwater in barrels, trading buckets between households, and rationing every clean litre. The irony is that ash, when wet, grows heavier, so the very rain that might refill barrels could also collapse roofs. Survival would mean balancing one hazard against another. Hospitals would occupy a precarious position. Generators provide a buffer, but fuel is finite. In a landscape where transport is crippled, resupply might never arrive. Doctors would likely return to practices not seen in centuries, operating by natural light, sterilizing instruments with boiling water instead of disposable plastics, triaging patients without access to modern imaging. Massacres would be scavenged and reused, improvised from cloth if necessary. The irony is that in an ash world, lung conditions would be the most common ailment, yet oxygen supplies would be the scarcest. Communities as a whole would adapt in unexpected ways. Towns cut off from external aid often fall back on local organisation. Neighbours form work crews to clear ash from critical structures, prioritising food warehouses, water treatment stations and shelters. Roads are dug out not for cars but for human passage, narrow lanes cleared by hand. The same spirit that once built frontier settlements could re-emerge, though in conditions far harsher than the pioneers ever knew. Social scientists who have studied disasters note that cooperation often spikes in the early aftermath, when people face a shared threat. In an ash world, this cooperation could be the only force keeping societies intact, yet adaptation would not be uniform. Some regions might recover quickly. Areas at the edge of the ashfall, where layers are thin, could resume agriculture within months once the ash is ploughed under. Ash is not sterile forever. In time, it weathers into soil enriched with minerals. But for regions buried in tens of centimetres, recovery would take years, and in places smothered by meters, lifetimes. Survivors in those zones would not wait for the land to heal. They would leave. Migration, not repair, would be the true adaptation strategy. In that sense, the ash world would not only be a geological disaster, but a demographic one. The United States has never faced an internal migration on such a scale, yet history offers small precedents. The Dust Bowl of the 1930s, when millions abandoned parched farms, the Irish famine of the 19th century, when starvation drove a quarter of a nation abroad. Ashfall would amplify these patterns, pushing millions from grey wastelands toward edges where air is breathable and food still grows. The question would not be whether humans can adapt in place, but whether political and social systems can absorb the mass movement of displaced populations. It is tempting to see these adaptations as grim, but they are also reminders of resilience. Humans have survived drought, plague, ice ages, and eruptions before. We are an improvising species, capable of reusing scraps, sharing burdens, and building order out of collapse. The ash world would test that capacity, not in the first fiery hours of eruption, but in the slow grind of weeks and months when patience, not panic, determines survival. The world would not end in a blast of fire but in a whisper of dimmed sunlight. If Yellowstone were to erupt in the way geologists classify as a super-eruption, the first days would be defined by pyroclastic flows and ashfall. But it is the following years that contain the true global hazard. The danger is not only what comes down, but what goes up. Sulfur dioxide thrust high into the stratosphere, beyond the reach of rain, lingering for years. What follows is not a local calamity, but a planetary rebalancing. The slow collapse of climate into something colder, darker, and less forgiving. And it begins almost invisibly. Sulfur gases are released in almost every volcanic eruption. In smaller events, like the basaltic eruptions of Hawaii, they irritate lungs and sting eyes, but stay close to the surface. In an eruption of continental scale, the gases are propelled far higher. Columns of ash and gas from a Yellowstone-scale event would rise into the stratosphere, where they react with water vapour to form sulfate aerosols, tiny droplets of sulfuric acid suspended in the sky. They act like a mirror. Instead of allowing sunlight to strike the surface, they reflect a portion back into space. It is not dramatic at first. The world does not suddenly go dark. Days remain bright. But the energy budget of the planet shifts downward. Even a reduction of 1 or 2% in solar radiation is enough to tug average global temperatures lower by several degrees. In climate, those few degrees are the difference between abundance and collapse. The mechanism is simple but merciless. Crops need warmth and predictable seasons. When summer is shortened or fails to arrive, harvests shrink. Wheat, rice, and maize are particularly sensitive, and these three grains supply the majority of global calories. If Yellowstone injected hundreds of millions of tons of sulfur into the upper atmosphere, growing seasons across the northern hemisphere could shrink for years. Frost could return in months normally reserved for planting, and rains could shift unpredictably. Farmers accustomed to centuries of climate stability would watch as once reliable schedules falter. In one valley, crops might fail from unseasonable cold. In another, storms might pound fields to mud. Hunger does not arise everywhere equally, but ripples outward from the most vulnerable regions first. History gives us case studies of volcanic climate disruption. While Tambora in the year 1815 produced a year without a summer, its sulfur load was small compared to what Yellowstone could expel. Ice core records suggest that super-eruptions can inject sulfur at least an order of magnitude greater than historic examples. Climate models built by atmospheric scientists in the 2000s show potential temperature drops of several degrees globally, with even sharper decreases in continental interiors. Oceans, which warm and cool more slowly, act as a partial buffer, but landlocked agricultural regions, like the American Midwest, Ukraine or northern China, would face the harshest contractions in growing season. The effects extend beyond temperature. Sunlight is not only heat, it is also photosynthesis. A thinner sun means plants fix less carbon, grow more slowly, and produce less biomass. Grasslands shrink, threatening livestock. Forests weaken, making them vulnerable to disease and pests. Even the colour of the sky changes. With sulfate aerosols suspended above, sunsets bloom red and purple for years, beautiful reminders of an underlying catastrophe. Beauty and famine arrive together. Global trade is not designed for this kind of prolonged shock. In our era, much of the world lives only weeks away from hunger. Grain reserves that once held years of security are now thin, trimmed by decades of just-in-time logistics. If several consecutive harvests collapse across major breadbaskets, the buffer is measured in months. Nations with surplus would hoard it. Nations dependent on imports would bid desperately. Prices would spike not linearly, but explosively. Food riots, once rare, would become weekly occurrences. In past centuries, volcanic famines could depopulate regions. In our century, with 8 billion mouths, the scale of vulnerability is unprecedented. There is also the paradox of the tropics. Equatorial regions might not cool as drastically, but monsoon systems are delicately tuned to the balance of ocean and land temperatures. Disturb that balance, and rainfall falters. India, Southeast Asia, and large portions of Africa depend on seasonal rains for agriculture. With aerosol haze overhead, monsoons could weaken or shift, leaving billions without predictable water. Crops may wither not from cold, but from absence of rain. Famines are not caused by one factor alone, but by overlapping stresses. Too little sun, too much rain in the wrong place, too little rain in others. Livestock cannot be ignored in this calculus. Grains feed not only humans, but animals, and when grain prices soar, so do meat and dairy costs. Wealthier societies could choose to divert grains to people rather than animals, collapsing livestock markets overnight. That decision, logical in terms of calories, would reshape diets globally. Billions would lose access to cheap protein. Malnutrition would rise even where outright starvation does not. And yet, while famine is the obvious killer, disease often follows close behind. Malnourished populations are more susceptible to epidemics. Ash-contaminated water supplies provide breeding grounds for pathogens. In the 19th century, cholera spread in the wake of climate disruptions. In a post-Yellowstone world, waterborne diseases would almost certainly surge. The health impacts would be magnified not only by weakened bodies, but by strained medical systems already coping with ash and infrastructure loss. Scientists modelling these outcomes emphasise uncertainty. Climate is not a simple switch, but a complex system. Some models predict drops in global average temperature of several degrees lasting a decade. Others suggest the aerosols could persist even longer, depending on how high they rise and how much sulfur is injected. The only certainty is disruption. No modern society has endured a volcanic winter of this magnitude. Fossil evidence, ice cores, and genetic clues hint at the stakes, but the details remain speculative. It is also worth stressing that recovery does occur. Aerosols eventually fall out of the sky. Sunlight returns. Soils enriched by volcanic ash can, in the long term, become more fertile. Forests regrow. Climate heals itself on timescales of decades. But survival during those decades is the challenge. For species in the wild, some will adapt, others will vanish. For humans, survival is mediated by politics, cooperation, and the ability to share food across borders. The geological hazard becomes a social test. The haunting question is not whether the planet could survive a Yellowstone winter, the Earth always survives. The question is how human civilization, tuned to delicate balances of trade, agriculture and climate, would withstand years of grey skies and short harvests. Could nations cooperate, or would famine fracture them? Would technology buffer us, or prove fragile under stress? The invisible haze above, silent and beautiful at dusk, would be the truest threat. Not the eruption itself, but the long dimming of the sun. Why spend so much time thinking about a volcano that almost certainly will not erupt in our lifetimes? The statistical odds are sobering but oddly comforting. The best estimates, grounded in geologic records and probability calculations, place the annual chance of a Yellowstone super-eruption at roughly 1 in 700,000. In other words, less likely than being struck by an asteroid, less likely than being killed by lightning, far less likely than almost any other hazard you can imagine. To treat Yellowstone as an immediate threat to civilization is to misunderstand probability. The Earth is dangerous, but it is not waiting to kill us tomorrow. And yet scientists continue to watch, to measure, to listen. The question is not so much whether Yellowstone will erupt in our time, but why we choose to pay attention to such remote possibilities at all. The Yellowstone Volcano Observatory exists for precisely this balance of humility and vigilance. Established in the early 2000s as a collaboration between the US Geological Survey, the University of Utah, and the National Park Service, the observatory maintains an array of instruments across the caldera. Seismometers register tremors, GPS stations track ground movement, gas sensors measure emissions, and satellites overhead record the tiniest changes in elevation. The data streams in continuously, analysed daily by teams of geophysicists. They are not looking for certainty. They know that geology resists prediction. What they seek instead is early warning. If patterns of uplift, seismicity, or gas release deviate sharply from the background hum of Yellowstone, alarms would be raised. Not to predict the exact hour, but to give societies time to adapt. The philosophy behind such monitoring is worth noting. Humans have only existed for a geological blink of an eye. Our civilizations are built on assumptions of stability. Rivers will keep flowing, seasons will keep turning, soils will keep producing. But the geologic record reminds us that stability is the exception, not the rule. Continents rift, glaciers advance and retreat, and volcanoes of unimaginable scale occasionally reset the climate. To ignore these truths is tempting. After all, most lifetimes pass without seeing such events. Yet to ignore them entirely is to court fragility. Monitoring is not paranoia. It is a quiet pact between our species and the deep earth, an agreement to pay attention even when danger is remote. Part of what makes Yellowstone unique is how visible its energy is. Most of Earth's supervolcanoes are buried, disguised beneath mountain ranges or hidden under oceans. Yellowstone bubbles and steams in the open, a reminder to every visitor that our planet is alive. To walk its boardwalks is to stroll across a pressure valve, to see hot springs and geysers as the surface symptoms of something vaster below. Few other places on Earth offer such a direct confrontation with planetary-scale processes. That confrontation explains, in part, why Yellowstone has become a focus of cultural fascination. It is not merely about geology. It is about the human tendency to stare at danger and find meaning in its silence. And so we return to the odds, 1 in 700,000. That number can be read two ways. Some interpret it as reassurance, too unlikely to worry about. Others hear it as inevitability. If not today, then one day. Both readings are true, depending on the timescale you choose. For an individual, Yellowstone is irrelevant. For a species measured across tens of thousands of years, it is inevitable. The eruption will come eventually, just as ice ages will come, just as continents will drift into new configurations. The real question is not whether, but when. And in that question lies a kind of existential comfort. To live as humans is always to be temporary, to borrow time from a planet whose processes dwarf our histories. Scientists emphasize another truth as well. Yellowstone is not the only threat, nor the greatest. Humanity faces more immediate dangers from climate change, pandemics, and the choices we make in managing our own technology. The fascination with Yellowstone should not distract from these, but it can offer perspective. By contemplating the rare, the catastrophic, the unimaginable, we sharpen our sense of proportion. We learn humility. We remember that the Earth's patience is measured in millions of years, not election cycles or business quarters. We remember that survival is not guaranteed, and yet we also remember that our ancestors endured upheavals, migrations and bottlenecks before. If they could persist through those, perhaps we can persist through ours. The deep time view is paradoxical. On one hand, it diminishes us, a species vulnerable to ash and aerosols, no more immune than rhinos in Nebraska or mammoths on Siberian plains. On the other hand, it elevates us, the only species known to measure, to model, to ask what if. To sit awake at night and imagine the 1 in 700,000 chance is uniquely human. We cannot control Yellowstone, but we can prepare, not by drilling or scheming to prevent it, but by strengthening the systems that help us endure shocks of any kind: food distribution, cooperation, adaptability. In this sense, Yellowstone is less a threat than a mirror. It reflects back our fragility and our resilience in equal measure. To watch Yellowstone, then, is not about expecting it to erupt tomorrow. It is about remembering that we inhabit a planet still forming, still breathing, still shifting beneath our feet. Our civilizations are temporary arrangements upon restless crust. The geysers that delight tourists are whispers from the mantle, gentle reminders that permanence is an illusion. The observatory's instruments, quiet and precise, are less alarms than listening devices, ears pressed to the ground of deep time. They do not predict doom. They cultivate patience. And maybe that is the most important reason to watch. In a world often consumed by noise, by urgency, by the daily cycle of crisis, Yellowstone pulls our gaze back towards scale. It asks us to measure not by days or years, but by hundreds of thousands of years. It asks us to imagine futures beyond our lifespans, to recognize that we are part of a story that does not end with us. In that sense, Yellowstone is not a threat but a teacher. Its odds remind us that safety is relative, that vigilance is wise, and that humility is necessary. So the next time you see steam rising from a hot spring, or read about a minor swarm of earthquakes under the park, you might pause. Not in fear, but in recognition. The Earth is restless. It always has been. The fact that we're here at all, perched on this thin crust, is improbable enough. That we can measure, model, and contemplate our own extinction-scale hazards is even more improbable. To be a thinking primate on a volatile planet is a strange fate, but it is ours. And if you cannot sleep tonight wondering whether Yellowstone is due, the answer is simple. Almost certainly not. The odds are distant, the monitoring is constant, and the Earth for now is quiet. But the deeper answer is more haunting. Yes, one day it will happen. Maybe in tens of thousands of years, maybe longer. Between now and then lies the span of civilizations yet to be born, discoveries yet to be made, stories yet to be told. To live with that knowledge is not a burden, but a reminder to stay curious, to stay humble, and to recognize that we are temporary guests on a planet that plays by its own rules. Thank you, fellow sapiens, for wandering this timeline with me, for drifting into deep time, for slowing down and remembering. If this helped you fall asleep, helped you study, or simply helped you step out of the noise for a while, thank you for being here. If you think more people should know this story, you know what to do. Like, subscribe, share it with the sapiens in your life, and tell me, are you listening before bed, while working, or somewhere in the world I can only imagine? And as always, stay curious, stay calm. I'll see you in the next story.